The information loss paradox in de Sitter space, a midnight mystery. Imagine this. You are tucked into bed, the world is silent, and your brain, ever the overachiever, decides it is time for a casual existential crisis. Somewhere between counting sheep and thinking about tomorrow's grocery list, a thought sneaks in. If the universe erases information, does anything we do really matter? Before we fall too deep into a cosmic rabbit hole, please take a moment to like this video, subscribe to the channel, and ring the notification bell for more gentle paradoxes, sleep philosophy, and relaxing mental puzzles. Also, feel free to share your midnight thoughts in the comments. I love reading them as I sip my third cup of sleepy time tea. Now, let us set the scene. Welcome to the information loss paradox, specifically in the mysterious landscape of de Sitter space. It sounds complicated because it is. But do not worry. Tonight, we are turning the mind-bending into something soft and cozy, like a weighted blanket for your overthinking brain. First, what is de Sitter space? In simple terms, de Sitter space is a model of the universe where everything is expanding at an accelerated rate. Imagine blowing up a balloon that gets bigger and bigger and never stops. Now imagine you are stuck on the balloon. That is de Sitter space. It is a favorite playground for cosmologists when they are feeling particularly mischievous. Now, sprinkle in a problem. In regular black holes, physicists like Stephen Hawking noticed something spooky. Black holes evaporate over time, and when they do, the information about what fell inside them seems to disappear forever. This was called the black hole information paradox, and it caused many smart people to stare into the distance for hours, wondering if reality was fundamentally rude. But it gets weirder. In de Sitter space, the entire universe behaves a little bit like a black hole. There is a kind of cosmic horizon, a boundary beyond which you cannot see because the universe is expanding too fast. And if you push some information past that horizon, it might be gone forever, deleted, as if it never existed, like your New Year's resolutions around February. Now the question becomes, if information can be lost in de Sitter space, what does that say about the universe, about memory, about meaning, and about that embarrassing thing you said in third grade that still haunts you at night? Here is where it gets spicy. In physics, there is a principle called unitarity, which basically says information must be preserved, always, no matter what. Even if it gets scrambled into a cosmic smoothie, somewhere, somehow, it is still there. But if information in de Sitter space can truly vanish, it breaks unitarity. It breaks a core promise of the universe. It would be like playing chess and suddenly realizing that the pawn you captured 3 moves ago just ceased to exist. Not captured, not stored, not hidden under the couch, just gone. No trace, no record, nothing. And now you are lying there, wondering, if information can be erased, can I be erased too? If the universe forgets, what is the point of remembering? It is bedtime, and you have accidentally opened a portal into the abyss. The information loss paradox in de Sitter space taps into our deepest fears. That meaning might not be eternal, that memory might be fragile, that existence itself might be more like a Snapchat message than an epic novel. The first person to really bring this flavor of existential dread into the mainstream was Stephen Hawking, who originally proposed the information loss in black holes. Many others extended the idea to de Sitter space, realizing that an expanding universe might be just as guilty of deleting things without forwarding them to the archive. And the arguments began. And they continue. Some physicists say, no, information cannot truly be lost. It must be stored somehow, maybe at the cosmic horizon itself, encoded like ancient hieroglyphs that only hyper-advanced beings could decode. Others say, actually, maybe the universe is allowed to delete stuff sometimes. Maybe we are the ones with unrealistic expectations. And then there are the radicals who say, who cares? Information is overrated. I cannot even remember where I put my car keys. Each camp has compelling points, and none have a perfect solution. Think about it like this. Imagine your brain is a library. Every memory, every fact, every feeling is a book. If you lose one book, say, you forget your fifth-grade teacher's name, you can accept it. But what if the entire library had a policy that said, every Tuesday we randomly burn some books and pretend they never existed? That would change the nature of the library. It would not be a reliable archive. It would be something else, something wobbly. This is the fear behind the information loss paradox, that the universe, at its core, is not the orderly, rule-following institution we hope it is. It might be more like a teenager's bedroom. Things appear, things vanish, no explanation. Good luck finding your left sock. Philosophically, it raises powerful questions. If memory is temporary, what does that say about identity? About morality? About love? Are these things rooted in permanence? Or are they beautiful precisely because they are fleeting? In a universe that forgets, maybe meaning comes not from longevity, but from presence. Maybe the universe is like a sand mandala, an intricate work of art painstakingly created by monks, only to be deliberately destroyed once completed. The beauty lies not in its endurance, but in the moment of its existence. That is a strangely comforting thought. Maybe we are not failed archivists. Maybe we are celebrated storytellers. There is also a twist lurking in the math. Some theorists propose that information might be preserved in strange, encrypted ways, hidden behind the cosmic horizon like a cosmic version of cold storage. Maybe the universe is sneakier than we thought. Maybe it does not lose information. It just hides it so well that, from our point of view, it is indistinguishable from being lost. This idea has a delightful name: holographic principle. It suggests that all the information contained within a region of space can be represented on the boundary of that region, like a hologram. Reality, in this view, is a projection from the edge. Yes, you heard that right. We might all be cosmic holograms. Sleep tight. In the end, no one knows for sure. Maybe information is preserved. Maybe it is lost. Maybe the universe is a teenager whose hard drive crashed and who is just too embarrassed to admit it. But whatever the answer, the paradox invites us to lean into wonder, to embrace mystery, to recognize that the universe might be bigger, stranger, and more alive than our tidy categories can capture. And honestly, is that not a beautiful thing? The next time your brain whispers a paradox into your sleepy thoughts, do not fight it. Smile. Float with it. Let it rock you gently into dreams. Because whether information is preserved or not, one thing is certain. Your existence tonight, in this moment, thinking these thoughts, that is real. And that is enough. Now, to close this chapter, let me leave you with one final image. If the universe forgets a bad haircut you got in high school, is that not proof that some cosmic mercy exists after all? The Many Worlds Paradox. A multiverse of maybes. There are days when life feels like an endless parade of choices. Coffee or tea. Take the bus or walk. Watch a documentary or binge an entire season of a reality show you will never admit to anyone. As you stand there, frozen in indecision over which cereal to buy, have you ever wondered, what if you chose both? What if there were other versions of you who did all the things you did not? Welcome, my friend, to the Many Worlds Paradox. The Many Worlds interpretation is one of the most captivating and sleep-resistant paradoxes in the entire universe. It is a favorite of physicists, philosophers, and late-night overthinkers alike. It slips effortlessly into conversations about quantum mechanics, multiverse theory, and why your dog sometimes stares at a blank wall as if he sees something you cannot. Let us start with a small, peculiar experiment. It is called the double-slit experiment. Scientists fire tiny particles, like electrons, at a barrier with two slits. If you observe which slit the particle goes through, it behaves like a tiny marble, picking a path. If you do not observe it, it behaves like a wave, going through both slits at once and creating an interference pattern. Yes, the universe behaves differently depending on whether you are watching. That is unsettling enough to make you rethink your webcam privacy settings. Enter Hugh Everett in 1957, a graduate student who looked at this weirdness and boldly proposed, what if, instead of the universe making a single choice, it makes every possible choice? In other words, every time a decision is made, the universe splits into multiple copies of itself. In one world you drink coffee, in another you drink tea, in another you move to Iceland to raise llamas and live off-grid. All real, all happening simultaneously, all unaware of each other. This is the many worlds interpretation. Not just a theory, but a gentle cosmic explosion of possibilities. At first glance, it feels comforting. You never miss out. Somewhere, somehow, every missed opportunity was seized by another version of you. But then the paradox creeps in like a cat, silently judging your life decisions. If every choice spawns a new universe, how many universes are there? An infinite number? Are there universes where gravity forgot how to work, where fish compose symphonies, or where you actually remembered to send that email on time? This raises awkward questions. What defines you? If copies of you exist in other realities, are they still you? Or are they completely separate individuals who just happen to share your DNA and questionable fashion choices? The many worlds. Paradox also shakes the foundation of probability itself. If everything happens somewhere, does anything matter? Does chance even exist? If in one universe you win the lottery, but in another you lose spectacularly, what does luck mean anymore? It becomes like playing a game where every outcome happens, and you are left with a participation trophy for simply existing. And there is an even more delicate thought. If every outcome plays out somewhere, are there universes where you made worse choices? Better ones? Ones you never imagined? Are there worlds where history turned out completely different? Where dinosaurs evolved intelligence and are now hosting their own late-night talk shows? Physicists have tried to calm our spinning heads by reminding us that the many worlds interpretation does not necessarily mean you can travel to these other realities. They exist in parallel, separated by an unfathomable cosmic firewall. You will never meet your alternate selves, which is probably for the best. No one needs the awkwardness of bumping into a version of yourself who actually followed through on New Year AS resolutions. At the heart of the paradox is this haunting question. If every possible version of you exists, what makes this version you? Is it continuity? Is it memory? Is it just the current playlist of experiences stitched together by your brain into the story you call your life? The many worlds. Paradox reminds us that our sense of identity is both precious and fragile. We think of ourselves as solid, consistent beings, yet quantum mechanics gently whispers that we might be more like ripples on a pond, fleeting, interconnected, and more complex than we could ever fully grasp. The theory also pokes at free will. If every decision creates a new universe, do you actually have choice? Or are you simply exploring one branch of an endless decision tree where every possibility has already been accounted for? It is like thinking you are steering the boat when you are actually on a river that splits into infinite streams, and you just happen to be on one of them. Some thinkers propose that we live comfortably in ignorance. Even if there are countless versions of us, we only experience this one timeline. Like watching a movie and knowing there are deleted scenes you will never see, we carry on as though ours is the only plot that matters. The many worlds interpretation has not only fascinated scientists, but has also inspired countless stories in popular culture. From science fiction novels to blockbuster films, the idea of parallel universes has given writers endless material to explore. It shows up in comic books, video games, and more recently, in discussions about artificial intelligence and simulated realities. The paradox remains unresolved because it is almost impossible to test. We cannot peek into another universe. We cannot shake hands with our alternate selves or borrow sugar from the version of us who wisely invested in cryptocurrency before it became a thing. Yet the beauty of the many worlds paradox is not in finding an answer. It lies in the gentle invitation to imagine, to wonder, To consider that the universe is vast, layered, and full of mysteries far beyond our limited senses. It asks us to reflect on our choices, not with regret, but with curiosity. Each path taken and not taken weaves together the rich tapestry of existence. Maybe your decision to eat pizza last night did not only affect your digestion, but also created an entire universe where you chose salad and saved yourself from midnight heartburn. In the end, the many worlds paradox is a cosmic mirror reflecting back the infinite possibilities of life. It reminds us that while we only get to walk one path, the knowledge that countless others exist can be strangely comforting. Perhaps it tells us that every moment matters. Every tiny decision is an affirmation of our unique journey through this corner of the multiverse. So tonight, as you drift off to sleep and your mind playfully wonders if another you somewhere else is choosing a different pillow, remember this. Even in a sea of endless versions, you are the only you living this exact life in this exact moment. And with that, I will leave you with one last thought. If in another universe, you already finished reading this chapter and understood everything perfectly, can you please send instructions back, preferably before my coffee gets cold? The Quantum Immortality Paradox. The most unsettling game of survival. There is something strange about an old light bulb. You flick the switch, and nothing happens. You shake it gently, flick it again, and suddenly it springs to life. You cannot help but wonder, did the light ever really die? Or was it only waiting for the right moment to shine again? Now imagine that light bulb is you. Welcome to the deeply eerie mystery of the Quantum Immortality Paradox. The Quantum Immortality Paradox comes from one of the wildest corners of theoretical physics and touches on the uncomfortable line between science fiction and reality. It all begins with quantum mechanics and its favorite party trick, the principle of superposition. Superposition tells us that particles at the quantum level do not have definite states until they are measured. An electron can exist in multiple positions at once. A photon can pass through two slits simultaneously. A cat can be both alive and dead if you are Erwin Schrödinger and you have a knack for strange thought experiments. Schrödinger's cat, of course, was never intended to be taken literally. His famous paradox was designed to expose the absurdity of applying quantum weirdness to everyday objects. Yet, decades later, the quantum immortality paradox pushes this unsettling logic further, much further. The idea first emerged from the many worlds interpretation, MWI, of quantum mechanics. Hugh Everett III proposed in 1957 that every possible outcome of a quantum event actually occurs, but in separate branching universes. Instead of randomness deciding an outcome, the universe simply splits and accommodates all possibilities. Now imagine you are an observer in a quantum experiment with a life or death outcome. Perhaps you are part of a theoretical quantum Russian roulette game, an experiment no sane person should try. In most universes, the trigger is pulled and you cease to exist. But in at least one universe, against all odds, the gun clicks harmlessly and you survive. In the next trial, the same thing happens, and the next, and the next. In every universe where you perish, you are not around to observe it. But in the one thread where you survive every time, you keep on living. From your perspective, you would be functionally immortal. This is the unsettling heart of the quantum immortality paradox. The observer never experiences their own death. You, the consciousness tied to a single timeline of unbroken survival, simply continue on, while all the other versions of you fall away in inaccessible branches of reality. It sounds both comforting and horrifying. Immortality might seem appealing at first, but this version comes with a cruel twist. It is not a guarantee of safety, health, or happiness. You would continue to survive every possible catastrophe, illness, accidents, disasters, but not without consequences. You could be battered, broken, or stuck in an endlessly worsening state, surviving but never truly living. The paradox forces us to reconsider the relationship between consciousness and reality. Does awareness require continuity? If every possible outcome exists somewhere, what does it mean to be you? Is your identity tied to the biological matter of your body or to the uninterrupted chain of your conscious experience? This leads to a far stranger possibility. You may already be the survivor. Think about all the times you narrowly avoided disaster. The missed bus that saved you from an accident. The almost slip on an icy sidewalk. The unexpected turn that prevented a collision. Could it be that you are, unknowingly, the version of yourself that has already defied countless unlikely odds? Of course, mainstream science firmly rejects any practical application of quantum immortality. It remains purely a thought experiment, an extreme consequence of taking the many worlds interpretation literally. There is no way to test it. You cannot design an experiment to prove it, because in every universe where you fail, you would not be there to report the result. This inability to verify or falsify quantum immortality places it outside the boundaries of accepted science. It exists in the same strange realm as philosophical puzzles, plausible within its own rules, but frustratingly unreachable from ours. Nevertheless, the paradox persists because it forces physicists and philosophers alike to wrestle with profound questions about death, survival, and personal identity. It forces us to confront the uncomfortable possibility that the universe may care very little about our human notions of finality. The quantum immortality paradox also connects with the deeply debated concept of observer-dependent reality. In quantum mechanics, observation influences outcomes. But if survival itself is dependent on observation, does that make consciousness the ultimate arbiter of existence? Some thinkers propose that quantum immortality offers a strange kind of optimism. If nothing else, it provides an extreme answer to the fear of non-existence. You may never know how many versions of you were lost along the way. Only that your awareness persists in the unbroken line of survival. Others view it as the most chilling form of isolation imaginable. An endless journey through misfortune, unable to escape because, by definition, you cannot. Survival becomes a curse rather than a gift. From a storytelling perspective, the quantum immortality paradox is irresistible. It has inspired numerous science fiction stories about unkillable characters, doomed loops, and endless survival against impossible odds. These tales offer haunting explorations of what it might mean to live forever when forever is a prison. Even in our everyday lives, the paradox provides an oddly poetic metaphor. Life itself is a continual series of narrow survivals. Every breath, every heartbeat, every seemingly mundane choice nudges you along one branch of countless possibilities. Whether or not quantum immortality exists in any meaningful way, it serves as a reminder of just how fragile and improbable life is, and how extraordinary it is that we are here to experience it. So tonight, as you close your eyes and surrender to sleep, consider the wonder of your own survival. Against impossible odds, you exist in this moment, on this branch of the great cosmic tree. That, alone, is something extraordinary. And now, to close this chapter, I will leave you with one final thought. If I really am immortal in at least one universe, I sincerely hope the other versions of me figured out how to remember where they left their car keys. The measurement problem, paradox. When reality refuses to make up its mind, you are standing at a crosswalk. The light is red, but no cars are coming. You hesitate, glance around, and step forward. At that very moment, the light turns green. You stop and laugh to yourself. Was the universe waiting to see if you would cross before deciding what the light should be? Welcome to the strange, slippery world of the measurement problem paradox. The measurement problem is one of the oldest and most irritating puzzles in physics. It sits quietly, never shouting, never demanding attention, yet it undermines the very foundation of how we understand reality. To grasp the paradox, you must venture into the world of quantum mechanics, where particles defy common sense at every opportunity. In the everyday world, objects behave predictably. A ball thrown into the air follows a smooth arc. A dropped spoon falls to the floor. Reality behaves whether you watch it or not. But in the quantum realm, particles exist in a ghostly blur of possibilities known as superposition. An electron can be here, there, or everywhere at once. A photon can travel multiple paths simultaneously. These particles do not seem to choose a definite state until someone measures them. That is the problem. The act of measurement collapses this superposition into a single outcome. Before measurement, the system exists in many states. After measurement, only one remains. The question physicists have struggled with for almost a century is, what exactly causes the collapse? Is it the act of looking? Is it the presence of a measuring device? Does it require human consciousness? Or does the universe just pretend to make up its mind at the last moment? This is not just an academic problem. The famous double-slit experiment shows the paradox in action. If you fire photons or electrons at a barrier with two slits and let them strike a screen behind it, an interference pattern emerges, a pattern created when waves interact. This suggests that each particle behaves like a wave, passing through both slits at once. But if you place a detector near the slits to observe which path the particle takes, the interference disappears. The particle suddenly behaves like a tiny billiard ball, going through only one slit. The act of measurement changes the outcome. That one fact has kept generations of physicists awake at night. Did the particle know it was being watched? Did it somehow adjust its behavior retroactively? Is there a hidden mechanism we have not discovered? Or does our very concept of reality need rewriting? The Copenhagen interpretation, first proposed by Niels Bohr and Werner Heisenberg, offered an unsettling answer. Particles have no definite properties until they are measured. Reality exists in a fuzzy blur of probabilities that only sharpens into a single outcome when we interfere. As long as nobody checks, the particle lives in its strange twilight zone of possibilities. But not everyone was happy with that answer. Albert Einstein famously objected. He could not accept a universe that relied on randomness and observation. "I like to think the moon is there, even if I am not looking at it," he once said. In response, some physicists turned to the many worlds interpretation. This radical idea, proposed by Hugh Everett, suggests that all possible outcomes happen, but in parallel universes. In one universe, the photon goes through the left slit. In another, it goes through the right. We experience only one branch, but the others continue existing just beyond our reach. Other proposals tried to eliminate the need for observation altogether. The de Broglie-Bohm theory, sometimes called pilot wave theory, says particles always have definite positions but are guided by an invisible wave. The wave influences the particle's path without any need for measurement-induced collapse. Then there is decoherence, a more recent idea that explains how interaction with the environment causes a system to lose its quantum weirdness and behave classically. According to this view, a particle becomes entangled with its surroundings, and its wave-like properties leak into the environment. As a result, only one outcome becomes accessible to us. Decoherence explains why we do not see cats in simultaneous alive and dead states or people walking through walls. But decoherence does not solve the central mystery. It describes how superpositions disappear, but not why a particular outcome occurs over others. The measurement problem remains unsolved because every interpretation leads to new, equally baffling questions. The paradox has enormous philosophical implications. What role does consciousness play? If reality only solidifies when observed, does human awareness actually help create the world around us? Or is observation simply another physical interaction, like an electron bumping into another particle? Some radical interpretations suggest that consciousness is woven into the fabric of the universe itself, while others dismiss this as metaphysical nonsense. The truth, at least for now, remains frustratingly out of reach. The measurement problem. Paradox also touches on the arrow of time. In classical physics, processes are reversible. You can run the equations backward and forward with equal success. But measurement introduces irreversibility. Once the wave function collapses, you cannot rewind the process. The future becomes locked in, and the alternatives fade into mathematical history. The paradox has not just stumped scientists, it has inspired artists, writers, and filmmakers. Countless books and movies explore the idea of parallel realities, alternate outcomes, and the mind-bending effects of observation. Every time a character travels between timelines or witnesses reality shift around them, the ghost of the measurement problem lingers in the background. In a strange way, the paradox offers a metaphor for our own lives. We live in a world of decisions. Every day, we collapse countless possibilities into choices. Will you go left or right? Call an old friend or forget? Speak or stay silent? Each choice becomes your personal measurement, selecting one future over infinite others. While physicists continue to argue over the measurement problem, most agree that quantum mechanics remains the most accurate and reliable theory we have. It powers lasers, computers, smartphones, and countless other technologies. The equations work. We just do not know why they work the way they do. So the measurement problem. Paradox remains, a soft whisper in the corner of reality, gently reminding us that we do not know as much as we like to think. As you drift off to sleep tonight, safe in your world of definite outcomes and stable objects, remember that deep beneath the surface, particles may still be dancing their quantum waltz of uncertainty, waiting for someone to look. And now, to close this chapter, I will leave you with one final thought. If nothing becomes real until observed, I would really appreciate it if my laundry pile decided not to exist until I decide to tackle it tomorrow. The Teleportation Paradox, the disappearing act with existential consequences. You are staring at your phone screen, waiting for a file to transfer. The little loading bar creeps forward, then freezes. You groan and think, why is everything so slow? Then your imagination drifts. What if you could transfer yourself like a file? What if you could just click and be somewhere else instantly? Welcome to the unsettling and fascinating riddle of the teleportation paradox. Teleportation has long been a beloved concept in science fiction. Whether it is Star Trek's famous "beam me up" command, or the countless futuristic movies where characters vanish and reappear somewhere else, teleportation feels like the ultimate convenience. No traffic, no airports, no weather delays, just a flawless hop from point A to point B. But the teleportation paradox asks a simple but terrifying question. If a machine disassembles you atom by atom and rebuilds you somewhere else, are you still you? Or did the real you just get destroyed and replaced by a perfect copy? To understand the paradox, let us first define how teleportation would work in theory. In the most common thought experiment, a teleportation machine scans every single detail of your physical structure, every molecule, every atom, every particle. It then transmits this information to another location where an identical copy of your body is created. The original you is disassembled, possibly vaporized, as part of the process. From the outside, nothing seems unusual. The person who steps out of the machine remembers their life, knows their family, has the same personality and quirks. To everyone else, it is the same person. But did your consciousness, your sense of self, travel along with the information? Or did the original you die in the process, leaving only a perfect replica to walk out the other side? This dilemma lies at the heart of the teleportation paradox. Some philosophers argue that continuity of consciousness is essential. According to this view, destroying the original you, even for the sake of creating a copy, effectively kills you. The person walking around afterward might look, sound, and act just like you. But they are not you. Your original stream of consciousness ended when the machine disassembled you. Others argue that identity is based on information and patterns, not on the specific material of your body. Our bodies replace cells constantly. You are not made of the same molecules you had 10 years ago, yet you still think of yourself as the same person. If the copy contains all of your thoughts, memories, habits, and emotions, does it even matter if the atoms are different? This is where things get complicated. Imagine two scenarios. In the first, a single copy of you is created elsewhere, and your original body is vaporized. In the second, the machine malfunctions and creates two copies, one at the destination and one still at the origin. Now there are two identical versions of you, both insisting they are the real one. Who is correct? Who has the right to your bank account, your home, your relationships? The teleportation paradox explodes into chaos. The paradox challenges our understanding of what makes you, you. Is it your physical matter? That seems unlikely since your body is always changing. Is it your memories and personality? That feels more intuitive, but the presence of two identical versions throws that answer into doubt. From a scientific standpoint, teleportation may seem far-fetched, but quantum teleportation has already been demonstrated on a very small scale. Physicists have successfully teleported the quantum state of particles like photons across distances by using quantum entanglement. However, this process does not transfer matter itself, only information about the state of the particles. So you do not have to worry just yet about waking up on Mars without knowing how you got there. Still, the prospect of teleportation raises real concerns about consciousness and personal identity. Imagine stepping into a teleportation machine, aware of the possibility that the original you might not survive. Would you dare to push the button? If the machine works as promised, no one else would ever know. Your friends and family would greet you at the destination none the wiser. But what about the you that steps into the chamber? Are you willing to gamble that your sense of self will transfer along with your molecules? The teleportation paradox also touches on the ethical and legal dimensions of identity. Would laws need to be rewritten to account for cases of duplicated individuals? What happens if someone teleports and then, for some reason, the destruction phase fails? Are both versions of the person legally entitled to the same rights and responsibilities? The paradox exposes a tangle of philosophical and practical questions that no one has answers for. Even though the idea of teleportation remains in the realm of science fiction for now, the paradox provides valuable insight into how we think about identity and the self. It forces us to confront an uncomfortable truth. We do not fully understand what makes someone the same person over time. This mystery has fascinated writers and filmmakers for decades. Countless stories explore the dark side of teleportation. Accidents that leave people merged with objects, duplicate selves fighting for survival, or the horror of realizing you were never the original to begin with. These narratives offer a chilling glimpse into the potential dangers of tampering with something as fragile as personal existence. In everyday life, the teleportation paradox also offers a strangely poetic metaphor. We are all, in a way, slowly teleporting through time. Our cells regenerate, our memories evolve, our bodies change. The person you were as a child is not physically the same as the person you are today, yet somehow, you remain you. The paradox suggests that the question of identity may be less about permanence and more about continuity. For now, teleportation remains an impossible dream, or perhaps a nightmare. The physics of scanning and recreating every particle in a human body is so far beyond our current capabilities that it may never be achieved. But the paradox remains relevant, reminding us how fragile and mysterious our sense of self really is. As you settle into bed tonight, safe in the knowledge that no one is going to accidentally teleport you to the next room, you can marvel at how little we understand about the very thing we take for granted, being you. And now, to close this chapter, I will leave you with one final thought. If teleportation ever becomes real, I'm putting it in my contract that my duplicate cannot show up to work meetings while I stay home in my pajamas. The heat-death paradox. When the universe slowly pulls the blanket over itself, you know the feeling. It is a chilly night and you curl deeper under your blanket. The warmth fades a little more with each passing hour, and no matter how tightly you pull the covers, the cold eventually wins. Now imagine the entire universe as that bed. Welcome to the profoundly unsettling but strangely poetic puzzle known as the heat-death paradox. The heat-death of the universe is one of the most sobering ideas in cosmology. It suggests that, far into the future, everything will settle into a state of maximum entropy where no usable energy remains. There will be no stars, no planets, no life, just cold, dark emptiness stretching forever. But the paradox lies not only in this grim prediction, but in the mind-bending question. How did the universe get here at all, if everything trends toward disorder? To fully appreciate the heat-death paradox, you have to meet its best friend and worst troublemaker, entropy. Entropy, in the simplest terms, is a measure of disorder. When things are highly ordered, entropy is low. When chaos reigns, entropy is high. A deck of cards stacked in perfect order has low entropy. Shuffle it into a random mess, and entropy soars. The second law of thermodynamics tells us that the total entropy of a closed system must increase over time. Translated into everyday language, this means that things fall apart. Ice melts, batteries drain, hot coffee grows cold. The universe is the ultimate closed system, and according to this rule, it should be headed straight for the cosmic equivalent of lukewarm coffee, maximum entropy. The early universe was incredibly hot, dense, and surprisingly low in entropy. It had a beautifully simple structure. Hydrogen and helium atoms formed, stars were born, galaxies spun into elegant spirals. Yet this smooth beginning feels contradictory. How could the universe start in such an improbably low entropy state when natural processes always lead to higher entropy? That is the first half of the heat-death paradox. The second half of the paradox comes when you fast forward billions upon billions of years. As stars burn through their fuel and galaxies drift farther apart, energy spreads thinly and uniformly across space. Black holes evaporate. Nuclear reactions cease. Eventually, everything reaches thermodynamic equilibrium. In this final state, temperatures are even, no energy differences exist, and no work can be done. The universe, once bursting with energy and structure, becomes cold and silent. But why would the cosmos evolve toward this melancholy finish line? The paradox forces us to confront an uncomfortable truth. Perhaps this slow decay was inevitable from the start. Or worse, maybe the laws of physics are rigged to ensure it. Physicists have tried to untangle this mystery for decades. One idea suggests that inflation, a rapid expansion that occurred just after the Big Bang, smoothed out any early irregularities and reset the universe into a low entropy state. Like spreading batter evenly across a pan before baking, inflation might have prepared the universe for the strange journey from order to disorder. Yet even this explanation leaves nagging questions. Why would a universe capable of producing dazzling stars, magnificent nebulae, and complex life be designed to fade into emptiness? Why set up a beautiful party only to guarantee that everyone leaves and the lights go out? The heat-death paradox also raises fundamental issues about time. We experience time as a one-way street. Eggs break, but do not unbreak. People age, but do not grow younger. This sense of irreversible time flow is deeply tied to entropy. It gives us the comforting illusion of progress and continuity. But in a universe that eventually erases all traces of its past, what does time even mean? Some scientists have proposed that the heat death may not be the final word. Theories such as the Big Bounce suggest that our universe could collapse back in on itself and trigger a new Big Bang. Others have speculated about pocket universes budding off from ours, carrying fresh, low-entropy conditions into their own timelines. And then there is the multiverse hypothesis. Perhaps our universe is only one of many, each with different laws and entropy rules. If so, the heat death of our universe might simply be a localized event in an unimaginably vast and active cosmic landscape. Even with these speculative ideas, no consensus exists. The heat-death paradox remains one of the most haunting and unsolved questions in physics. Outside the lab and observatory, the heat-death paradox touches something profoundly human. It reminds us of our temporary place in the cosmos. The idea that everything we build, love, and create will eventually vanish into cold darkness is deeply unsettling. Yet it also gives us reason to appreciate the present. The fact that stars still shine, planets still orbit, and life still thrives means we are living in a rare, precious era where the cosmic engine has not yet run down. Writers and filmmakers have often tapped into this paradox for dramatic storytelling. Tales of dying stars, civilizations racing against time, or desperate scientists trying to stave off universal decay all find their roots in the uneasy whisper of the heat-death paradox. In a way, it also serves as a metaphor for personal life. Everything we know changes. Youth fades, empires fall, trends come and go. But within that impermanence lies the beauty of fleeting moments. The very fact that things do not last makes them more valuable. The heat-death paradox challenges us to face the possibility that existence itself may be temporary. Yet it also offers a kind of cosmic humility. We may not control the ultimate fate of the universe, but we do have control over how we spend our brief window of warmth and light. So tonight, as you settle into your own cozy corner of this still vibrant universe, take comfort in the fact that the stars are still out, the planets still spin, and there is still time to wonder, to explore, and to dream. And now, to close this chapter, I will leave you with one final thought. If everything really will cool down and fizzle out someday, I hope the universe will at least remember to unplug my phone charger before it shuts off the lights. The Borel paradox, when probability starts acting suspicious. You are tossing a dart at a map pinned to the wall. You close your eyes, throw with all your might, and hear the soft thud of success. You open your eyes only to realize that your dart has landed exactly on the border between two countries. Now you are stuck wondering, which country should you count it for? Congratulations, you have just stumbled into the spirit of the Borel paradox. At first glance, probability seems like one of the more honest areas of math and science. Roll a die, flip a coin, shuffle a deck. Probabilities feel neat, logical, and fair. But when you step into the strange world of infinite sets, continuous spaces, and conditional probabilities, the whole system starts to wobble. The Borel paradox is one of those moments where probability quietly shrugs and says, "It depends on how you look at it." The Borel paradox first surfaced in the early 20th century, named after French mathematician Émile Borel. It emerges when you try to condition probability on an event that has a probability of 0. In normal circumstances, conditional probability is a useful tool. It answers questions like, what is the chance it rains, given that you see dark clouds? But conditioning on a 0 probability event is like trying to divide by 0. Things get strange very quickly. Imagine you are randomly picking a point on the surface of a perfect sphere. No preferred directions, no landmarks. Every point is equally likely, right? Now you decide you want to condition your selection on a very specific line, the equator, for instance. What is the probability that the point you picked lies on the equator? Since the equator is just a one-dimensional line on a two-dimensional surface, the probability of landing exactly on it is 0. But suppose you somehow condition on the event that you have picked a point on the equator. Now you can ask, what is the probability that your point lies at a particular longitude on the equator? Here is where the Borel paradox laughs gently in your face. Depending on how you define random when picking points on the sphere and then conditioning on the equator, you can get totally different answers. If you approach the equator vertically from the poles, your probability distribution will look different than if you approach it horizontally. The very way you set up the problem changes the outcome. In short, the method of conditioning matters, and in the Borel paradox, it matters a lot. It is a deeply uncomfortable result because it tells you that probability can lose its objectivity when dealing with continuous spaces and 0 probability events. Physicists and mathematicians hate this kind of instability. They want their theories to be rock solid, not dependent on arbitrary choices of framing. Yet the Borel paradox reminds everyone that in the infinite playground of continuous spaces, logic itself needs a little more care than usual. At its heart, the Borel paradox teaches a humbling lesson. The way you describe a problem shapes the solution you get. There is no single, universal correct answer. When you start conditioning on events of 0 probability, without carefully specifying your method, you must define your assumptions clearly, or you risk slipping into paradox without even realizing it. This issue appears not just in mathematics, but also in cosmology, physics, and statistics. When scientists model the universe or work with infinite ensembles of particles, they must be cautious about how they define probability measures. Otherwise, they might end up predicting absurdities just because they framed their models in slightly different ways. It even pops up in discussions of anthropic reasoning. the idea that our existence as conscious observers tells us something about the universe. If you try to condition on the event, "I exist in this kind of universe," without a clear probability framework, you risk wandering into the same swamps of ambiguity that the Borel paradox warns about. The paradox does not just haunt theoretical corners of science. It also has echoes in everyday life, although in less obvious ways. Anytime you draw conclusions based on extremely unlikely events, winning the lottery, surviving a plane crash, getting hit by lightning, you are implicitly dancing with conditioning on rare outcomes. The Borel paradox gently taps your shoulder to remind you that you must be very careful when interpreting these rare events. In popular culture, the Borel paradox has not yet become a movie villain or a plot device, probably because explaining it in an action scene would be tricky. Quick, redefine the conditional probability density before the reactor blows. But its philosophical implications quietly influence how we think about randomness, fairness, and meaning. In a deeper sense, the Borel paradox hints at something profound about human perception. We love to create stories based on rare events. We marvel at coincidences. We are astonished when someone wins the lottery twice. But the universe may simply be much messier and probabilities more slippery than our intuition can easily handle. Scientists deal with this slipperiness by being painstakingly careful. They define probability measures precisely. They avoid conditioning on zero probability events unless absolutely necessary, and when they must, they specify their method in painful detail. These safeguards protect against the chaos that the Borel paradox can unleash. But for the rest of us, the Borel paradox offers a humbler takeaway. When dealing with probabilities, especially in infinite or continuous settings, reality might not behave as cleanly as we would like, and sometimes, the way we ask a question shapes the answer we get more than we realize. The paradox also invites philosophical reflection. If reality itself can offer different answers depending on how you frame the question, what does that say about objectivity? Are facts independent of observers? Or does context inevitably creep into every measurement, every probability, every interpretation? The Borel paradox does not resolve these questions. It just sits quietly at the edge of probability theory, gently tugging at our certainties. So tonight, as you drift into the quiet randomness of sleep, remember that somewhere, in some corner of mathematics, probability is still having a polite identity crisis. And the next time you flip a coin or throw a dart, take a moment to appreciate that even in the simplest games of chance, the universe hides layers of complexity just waiting to surprise you. And now, to close this chapter, I will leave you with one final thought. If probability depends that much on how you look at it, I am starting to think that my chances of finding matching socks in the morning are secretly being sabotaged by math itself. The Simulation Hypothesis Paradox. When reality might be running on someone else's computer. You wake up to the familiar sound of your alarm. You brush your teeth, check your phone, and sip your coffee. Everything feels normal, solid, predictable. Then you notice something odd. The clock on the microwave says 6:17, but your phone says 6:12. A glitch? You shrug it off. But somewhere in the back of your mind, a small voice whispers, "What if none of this is real?" Welcome to the deeply unnerving thought experiment called the Simulation Hypothesis Paradox. The simulation hypothesis suggests that everything you see, touch, and experience, including yourself, might be part of a highly advanced computer simulation created by a civilization far more technologically sophisticated than ours. What feels like concrete reality may be nothing more than an elaborate virtual environment running on an unimaginably powerful machine. This idea, while wild, did not begin as science fiction. It was philosopher Nick Bostrom who, in 2003, laid out a logical argument that captured the imagination of scientists and philosophers alike. Bostrom reasoned that if a civilization ever became advanced enough to simulate entire worlds, they would probably create many such simulations. In that case, the number of simulated worlds would vastly outnumber the one real world. Statistically, you are more likely to be living in a simulation than in base reality. That is where the paradox begins. The simulation hypothesis. Paradox raises the mind-bending question: if we are inside a simulation, can we ever know it? And even if we somehow prove it, what could we do about it? Would we even want to know? Some scientists and thinkers have proposed ways to test the theory. They suggest looking for glitches or anomalies in the laws of physics, the way an old video game sometimes freezes when overloaded. Perhaps the speed of light or the fine structure constant is set at certain values because of programming constraints. Perhaps cosmic rays scatter in odd ways because the simulation engine occasionally needs to conserve computing power. These are fascinating suggestions, but so far, no such evidence has been found. The laws of physics appear consistent and stubbornly real. Still, the possibility remains tantalizing. The simulation hypothesis cannot be conclusively proven or disproven, which places it in the peculiar realm of philosophical paradox. This leads to even deeper questions about existence and consciousness. If you are a digital construct living inside a simulation, does that make your experiences less real? If your thoughts, emotions, and memories are lines of code running in someone else's server farm, does that make them any less meaningful? From a functional standpoint, probably not. You feel hunger, joy, sadness, love, and laughter. You experience reality the way any biological creature does. Whether your atoms are physical particles or simulated data, the experience itself remains real to you. Reality, it seems, may be defined more by perception than by material composition. The simulation hypothesis also draws intriguing parallels with older philosophical ideas. In ancient Greece, Plato described a world where prisoners chained inside a dark cave mistake shadows on the wall for reality. The simulation hypothesis is the digital age update of that allegory. You might be staring at beautifully rendered shadows and never realize there is a whole other level of existence outside the walls of your experience. Some have compared the idea to Descartes' famous proposition, "I think, therefore I am." Even if you are simulated, the very act of questioning your existence confirms some form of existence. Whether you are carbon-based or code-based, the consciousness doing the thinking is, in its own way, real. Yet the paradox persists. If we live in a simulation, what is the purpose? Are we part of a scientific experiment? A historical recreation? A very sophisticated video game? Are we the center of attention or simply background characters in someone else's world? The idea that we might be non-player characters in a cosmic sandbox is as humbling as it is terrifying. Even worse, what happens if the simulation ends? Could the architects simply pull the plug, causing everything you know to vanish in an instant? It is an existential cliffhanger with no satisfying answer. The paradox also touches on the limits of science. Science is based on observation and measurement. But if your instruments, your senses, and your very notion of space and time are all part of the simulation's programming, can you ever step outside the system to test it? The answer so far seems to be no. For these reasons, many scientists dismiss the simulation hypothesis as untestable and therefore unscientific. Others keep it on their mental shelf labeled interesting but unprovable. The simulation hypothesis has captured popular culture like few other ideas. Films such as The Matrix and books like Neuromancer play with the concept of hidden realities behind what we perceive as truth. Video games themselves offer a small taste of simulated worlds where characters move, interact, and even think within the rules of their programmed universe. The paradox also gives us a unique mirror for reflecting on human behavior. If you knew you were in a simulation, would it change how you live? Would you feel free to make bold decisions, knowing that your world might not be real in the traditional sense? Or would the knowledge make every moment feel even more precious, since this version of existence is all you have? From a philosophical angle, the paradox may offer an odd kind of comfort. If reality itself is simulated, then it proves how deeply meaningful simulated experiences can be. Joy, love, friendship, beauty, all are real within the context of the world you know. In a very real sense, the simulation hypothesis paradox reminds us that we have always been seeking the nature of reality. From ancient myths to cutting-edge physics, humans have never stopped asking, what is real? Where did we come from? What does it mean to exist? The simulation hypothesis does not give us answers. It offers only a possibility, one that forces us to examine everything we believe about our world and ourselves. It invites us to think bigger, to explore deeper, and to stay humble in the face of mystery. So tonight, as you shut off your devices, turn out the lights, and settle into bed, remember that whether you are made of atoms or algorithms, you are still you. Your story, your experiences, your life, they matter, even if reality is a complex program running on someone else's supercomputer. And now, to close this chapter, I will leave you with one final thought. If I really am living in a simulation, I would like to file a small complaint. Could the programmers please do something about my neighbor's lawnmower at 7 a.m. on weekends? The flatness problem in cosmology. When the universe walks the tightrope of perfection. You walk into a room carrying a tray stacked high with glasses of water. Every step you take feels like a gamble. Lean a little to the left, and everything crashes down. Shift slightly to the right, and the disaster repeats. Only by balancing perfectly do you avoid the mess. Now imagine the universe had to do the same, but for billions of years, across billions of light years. Welcome to the remarkable and baffling riddle known as the flatness problem in cosmology. The flatness problem deals with the shape of the universe itself. When scientists talk about a flat universe, they do not mean flat like a pancake or a sheet of paper. They mean flat in the sense of geometry. A flat universe follows the rules of ordinary Euclidean space. Parallel lines never meet. Triangles add up to exactly 180 degrees. Light travels in straight lines across vast cosmic distances. The other options are far stranger. If the universe had positive curvature, like the surface of a sphere, parallel lines would eventually meet. If it had negative curvature, like a saddle, lines would diverge away from each other. But observations show the universe is astonishingly flat. The problem is, it should not be. To understand why, we must rewind to the beginning. The Big Bang. After the Big Bang, the universe expanded rapidly, and its density determined its curvature. If the density had been ever so slightly higher, the universe would have curved back in on itself and collapsed into a big crunch. If it had been just a bit lower, it would have expanded too fast and become cold, empty, and lifeless. It is as if the universe balanced on a cosmic knife's edge. The numbers are staggering. Physicists estimate that at 1 second after the Big Bang, the density of the universe had to be within 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros of the critical density required for flatness. That is like shooting an arrow across the universe and hitting a 1-inch target on the other side without missing. The precision required seems beyond belief. This extreme fine-tuning is what gives rise to the flatness problem paradox. Why did the early universe start off so incredibly close to perfect flatness? Was it luck? Or is there some deeper reason? For decades, this question bothered cosmologists. Then, in the early 1980s, physicist Alan Guth proposed an explanation: cosmic inflation. According to inflation theory, a tiny fraction of a second after the Big Bang, the universe expanded exponentially, doubling in size over and over again at breakneck speed. This rapid inflation smoothed out any wrinkles, curves, or irregularities. It is as if the universe started as a crumpled piece of paper and then inflated into a perfectly smooth, flat sheet. Inflation solves the flatness problem elegantly, but it introduces new mysteries. What caused inflation? What made it stop? Did inflation happen everywhere, or just in our observable universe? These are questions that remain unanswered. Even with inflation theory, the flatness problem still fascinates scientists because the precision of the early universe remains mind-blowing. Tiny fluctuations during inflation eventually became the seeds for galaxies, stars, and planets. Without near-perfect flatness, the complex structures we see today could not have formed. The cosmic microwave background, CMB, a faint afterglow of the Big Bang, offers more clues. In the 1990s, data from NASA's COBE satellite and later from WMAP and Planck missions showed that the geometry of space is remarkably flat, within tiny margins of error. These observations support inflation, but they also deepen the wonder at how finely tuned the universe really is. The flatness problem touches on another fundamental question. Why does anything exist at all? If the universe had collapsed or expanded uncontrollably, life would never have had a chance. Our existence seems to depend on this improbable balancing act. Some physicists wonder if we live in a multiverse, a vast collection of universes, each with different properties. In this view, we just happen to live in the lucky one that got flatness right. But the multiverse idea comes with its own philosophical baggage. If other universes are unobservable, can they ever be considered part of science? Or are they purely speculative? The flatness problem encourages such questions, making it one of the most thought-provoking paradoxes in cosmology. For ordinary people, the idea of a flat universe can be difficult to visualize. We tend to think of space as empty and unshaped, but cosmologists think of space as something that can bend, curve, or stay flat depending on its energy and matter content. The fact that we live in a universe where space is balanced so perfectly still feels like cosmic magic. The flatness problem also reflects on our place in the cosmos. It reminds us of the fragile, delicate conditions that allow our existence. The universe does not owe us this precision, yet here we are, sitting comfortably on a planet orbiting a stable star in a galaxy, drifting quietly through a vast, flat expanse. Writers and filmmakers have yet to fully explore the flatness problem in popular culture, probably because explaining fine-tuned cosmic geometry is harder to dramatize than black holes or time travel. But the paradox holds tremendous power as a metaphor. Life itself often feels like walking a tightrope. Too much or too little of anything, water, warmth, stability, and life falters. In this sense, we are all living examples of the flatness problem. In daily life, the paradox offers a humbling perspective. We worry about small things, deadlines, errands, lost keys. The flatness problem reminds us that the very fabric of space had to cooperate to extraordinary precision just for those everyday frustrations to exist. The paradox remains unsolved in many ways. Even with inflation as a leading theory, physicists continue to search for better data and alternative explanations. Experiments and observations of distant galaxies and the cosmic background radiation continue to test inflation and refine our understanding of the early universe. In the end, the flatness problem stands as a quiet monument to the beauty and strangeness of reality. It reminds us that even the vast emptiness between stars holds secrets that defy easy explanation. So tonight, as you lie under a peaceful sky dotted with stars, remember that you live in a universe that balanced itself on a cosmic razor's edge just to give you the chance to stare up in wonder. And now, to close this chapter, I will leave you with one final thought. If the universe really did fine-tune itself that perfectly, I would appreciate if it could apply just a fraction of that precision to my attempts at cutting wrapping paper in a straight line. The twin paradox, when time plays, favorites. You are at the train station, standing with your twin. The train pulls in, sleek and futuristic, gleaming under the station lights. Your twin hops on with a wave, heading out on a high-speed journey. You stay behind, sipping coffee and scrolling through your phone. Hours pass. The train returns and your twin steps off looking oddly youthful. No, you did not age poorly. Time itself played favorites. Welcome to the strange, reality-bending puzzle known as the twin paradox. The twin paradox is one of the most famous and unsettling consequences of Albert Einstein's theory of special relativity. It explores what happens when two people experience time differently because of relative motion. At first, the paradox seems simple, even whimsical, but dig deeper, and it challenges our understanding of time, space, and reality itself. Here is how it works. Imagine two identical twins, Alex and Jamie. Alex stays on Earth, living a normal life with birthdays, groceries, dentist appointments, and traffic jams. Jamie boards a spaceship and travels at nearly the speed of light to a distant star, and then returns. When Jamie steps off the ship, less time has passed for them than for Alex. Jamie is younger. The difference can be dramatic. While decades might pass for Alex, only a few years may have passed for Jamie. The cause of this strange age gap is time dilation. According to special relativity, as an object approaches the speed of light, time slows down for it relative to a stationary observer. For Jamie, the years of space travel felt ordinary. For Alex, those same years stretched much longer. The twin paradox arises when we consider perspective. From Jamie's point of view, they were at rest while Earth sped away and returned. Why should Alex not be the younger one? This symmetrical reasoning is what creates the paradox. The resolution lies in understanding that the twins do not have equivalent experiences. Jamie's journey involved acceleration and deceleration, changing direction in space.
Alex remained in an inertial frame, a frame of reference that is not accelerating. Special relativity only applies cleanly to inertial frames. Jamie's acceleration broke the symmetry, making Jamie the traveler and Alex the stay-at-home reference point. Once this asymmetry is recognized, the paradox evaporates. But the implications remain astounding. Time is not absolute.
It flows at different rates for different observers depending on their motion and gravity. What seems like a universal constant is really a flexible, observer-dependent experience. This is not just theoretical. Scientists have measured time dilation in real-world experiments. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. The effect is tiny at our everyday speeds, but it matches Einstein's predictions perfectly. The twin paradox also hints at the even stranger possibilities of general relativity, Einstein's later theory of gravity. In general relativity, time also slows down in stronger gravitational fields. This means that a clock at sea level ticks more slowly than a clock on top of a mountain. We do not notice because the difference is minuscule, but it is real. The twin paradox serves as a gateway to thinking about these distortions of time. It forces us to confront a reality that is fundamentally different from our everyday intuition. Time is not the universal, unstoppable force we assume. It is more like a flexible fabric that bends and stretches depending on where you are and how fast you are moving. Over the decades, the paradox has inspired endless debates, thought experiments, and even fictional stories. Writers and filmmakers love to explore the emotional consequences. Imagine returning home to find your friends and family aged far beyond you, to walk familiar streets that have changed completely, to be a visitor in your own life. That eerie loneliness captures the heart of the paradox. Some scientists have proposed extended interpretations of the twin paradox involving black holes or wormholes. In these versions, a traveler ventures close to a black hole, where gravity warps time so dramatically that they could return to Earth having aged only hours, while centuries passed for everyone else. The physics holds up, though the engineering required to pull off such a journey is, to say the least, unavailable. Another popular twist involves wormholes, hypothetical shortcuts through space-time. If a traveler used a wormhole to bypass vast distances, they might experience vastly different aging compared to someone who stayed behind. Again, the math works, but the practical details remain firmly in the realm of theory. The twin paradox also touches on philosophical questions. What does it mean for time to be relative? If two people can experience completely different durations between two events, what is now? Is there such a thing as universal simultaneity? According to relativity, the answer is no. What is now for you may not be now for someone speeding away at near light speed. The paradox highlights the strange relationship between motion and measurement. It reminds us that our most basic intuitions, like the idea that time flows the same for everyone, are based on our limited, low-speed, earthbound experience. The universe plays by different rules, even for those who never plan to leave the planet. The twin paradox affects modern technology. The Global Positioning System, GPS, would not work without accounting for both special and general relativistic effects. The satellites orbiting Earth move fast and experience weaker gravity than people on the ground. Engineers must correct for time dilation to ensure that your GPS directions do not send you into a lake instead of the grocery store. Despite being resolved mathematically, the twin paradox remains one of the most beloved teaching tools in physics. It forces students to let go of their assumptions and embrace the counterintuitive beauty of relativity. It illustrates how science can reveal a world that is far stranger and richer than common sense would suggest. So tonight, as you drift into sleep, safe in the gentle passage of time that feels the same for everyone in your neighborhood, remember that the universe does not guarantee that stability. Out there, somewhere, time may be bending, stretching, or ticking along at a pace completely different from yours. And now, to close this chapter, I will leave you with one final thought. If traveling near the speed of light means I would age more slowly, I think I have just found the ultimate excuse for being late to every appointment forever. The Cosmic Censorship Paradox. When the universe hides its most embarrassing secrets, you are throwing a party. The music is loud, snacks are disappearing fast, and guests are having a great time. Suddenly, a disaster strikes. A giant wine spill right in the center of the white carpet. Before anyone notices, you shove a table over it, neatly covering the mess. You exhale with relief. Crisis averted. Strangely enough, the universe may do the same thing with its most catastrophic disasters. That brings us to the strange puzzle known as the Cosmic Censorship Paradox. The Cosmic Censorship Paradox comes from the world of black holes, those mysterious cosmic vacuum cleaners that swallow everything around them, including light. At the center of every black hole lies something that terrifies physicists: a singularity. A singularity is a point of infinite density where space, time, and the known laws of physics simply stop making sense. All of our mathematical tools fail. It is the cosmic equivalent of an error message blinking furiously on your screen. Now, here is where things get tricky. In theory, singularities should exist in the universe, but nature seems to have a strange habit of protecting us from their chaos. According to Roger Penrose, who first proposed the idea in 1969, the universe might always cover up its singularities behind an event horizon, the boundary of a black hole beyond which nothing escapes. The mess stays hidden, just like your wine stain under the table. This idea became known as the cosmic censorship conjecture. It states that singularities cannot be naked, meaning they cannot exist where outside observers could see them. They must always remain decently dressed behind an event horizon. But is that always the case? That is the paradox. The cosmic censorship paradox arises because no one has been able to prove the conjecture for all possible situations. There are certain exotic solutions to Einstein's equations where naked singularities might exist. In these strange scenarios, the universe does not cover its mess, and the singularity is exposed for all to see. Why is that terrifying? Because if a singularity were exposed, it could, in theory, disrupt the very predictability of the universe. The equations that govern physics would break down in that region. Cause and effect would lose meaning. You could throw a rock and have no way to predict where, or even if, it would land. This nightmare scenario would violate the principle of determinism, the bedrock of classical physics. Determinism says that given the present state of a system, the future evolution of that system should be predictable. A naked singularity laughs at that idea.
Physicists have spent decades arguing whether naked singularities could ever form in nature. So far, observations have been on the side of cosmic modesty. All known singularities, such as those inside black holes, remain carefully hidden from view. The cosmic censorship paradox, however, refuses to go away.
Some theorists believe that under extreme conditions, perhaps in the collision of two black holes, or in certain high-energy particle interactions, nature might accidentally forget to cover the singularity. Others propose that quantum effects, which we still do not fully understand, might come to the rescue at the last moment and prevent naked singularities from forming. This leads to the connection between the cosmic censorship paradox and one of the greatest challenges in physics: uniting general relativity, which describes gravity and large-scale structures like stars and galaxies, with quantum mechanics, which governs the microscopic world. The two theories do not play nicely together, and singularities are where their clash becomes unavoidable. The paradox also raises philosophical questions. What does it mean for the universe to hide its singularities? Is the event horizon an actual cosmic curtain, or just a boundary that our limited senses cannot cross? Does the universe have an inbuilt safeguard system, or are we simply lucky so far? The concept of cosmic censorship captures the imagination because it offers a rare glimpse into the universe's sense of decorum. It suggests that there may be rules about what can and cannot be seen, but whether those rules are absolute or just highly recommended remains unknown. In the 1990s, some mathematical models suggested ways naked singularities could arise. These theoretical experiments involved unusual matter distributions or carefully tuned initial conditions. However, such scenarios seem unlikely to occur naturally. More recent work, using computer simulations and advanced mathematical techniques, continues to explore whether cosmic censorship holds under every possible condition. So far, no definitive counterexample has been found, but neither has the conjecture been universally proven. The paradox has yet to appear prominently in popular culture, likely because explaining a breakdown of predictability due to a visible singularity does not lend itself easily to blockbuster movie dialogue. Still, it remains a favorite among physicists and cosmologists for its mysterious, unresolved nature. The cosmic censorship paradox even invites speculation about the limits of human knowledge. Could there be regions of the universe forever beyond our understanding? Are there cosmic events happening that we can never detect, hidden safely behind event horizons? Or is the universe simply better at cleaning up after itself than we give it credit for? For ordinary life, the paradox does not have immediate consequences. Black holes are safely distant, and naked singularities, if they exist, are not expected to pop up near your neighborhood coffee shop. But the very existence of this paradox serves as a reminder of how incomplete our understanding of reality still is. It is humbling to realize that despite all our scientific achievements, there are still corners of the cosmos where the rules remain unclear. The cosmic censorship paradox stands as a quiet warning. The universe may hold surprises that even our most brilliant theories cannot yet explain. So tonight, as you gaze up at the dark sky, remember that somewhere out there, the universe may be very politely keeping its deepest mysteries covered, just out of sight. And now, to close this chapter, I will leave you with one final thought. If the universe really is that good at hiding catastrophic messes, I am seriously considering hiring it to help me organize my closet. The delayed choice quantum eraser paradox. Let us drift once more into that liminal space between wakefulness and wonder, where the mind cannot help but ask impossible questions, like, what if a single particle could decide its own history? Imagine you are lying in bed. The night is quiet, but your thoughts are snoring loudly. If light can behave both like a wave and like a particle, what happens when you tease it about which one it is and then quietly change your mind? Welcome to the delayed choice quantum eraser paradox, a gentle tickle at the edges of reality, and one of the most mind-bending quantum paradoxes ever to warp its way into your dream journal. Consider the classic double-slit experiment. You shine a beam of light or fire single photons, like very polite quantum postcards, at a barrier with two slits. On the other side, a detector screen waits to record an interference pattern, that familiar scalloped fringe that screams "wave" louder than a toddler denied dessert. If you peek at which slit each photon passes through by placing detectors, the interference pattern vanishes, replaced by two boring blobs of impacts, photons acting like particles. That is the wave-particle duality dance, a central theme in quantum mechanics explained in textbooks, lectures, and very occasionally on late-night science shows. But do not drift off yet. The delayed choice twist is where the fun begins. In 1978, Physicist John Wheeler asked, "What if the decision to look at the photon's path, or not, is made after the photon has already passed the slits? Could the photon retroactively choose to be a wave or a particle based on a future measurement? It is as though you ate a cookie at bedtime, then decided tomorrow morning whether you wanted to sneak it or confess, and somehow that future choice changed the very act of munching." Wheeler's thought experiment crashed into the shores of our common sense and left footprints that lead backward in time. Wheeler's original proposal was nearly impossible to build, but clever experimentalists have since realized it. They send photons through a double slit, split them into signal and idler photons, and route the idler photons through a labyrinth of beam splitters and detectors, a quantum funhouse. The signal photons go straight to a screen, recording hits. The idler photons can be detected in ways that either reveal which path information or erase it. Crucially, the choice to erase or reveal can occur after the signal photon has already hit the screen, thanks to cleverly engineered delays. Here is the gentle paradox. If the which path information is erased, the signal photons conspicuously display an interference pattern, as if they had always been waves. If the which path information is preserved, the interference vanishes, and the photons behave like particles. All of this happens even though the choice about the idler photon is made after the signal photon has already been detected. It is as though the photon looked at the future and said, "Very well, I will be a wave after all." This delayed choice quantum eraser experiment does not actually allow messages to be sent backward in time. You cannot use it to dial up Julius Caesar or warn yourself to bring an umbrella. The key is that you only see the interference pattern after you correlate the signal and idler detections in a joint data set. Individually, each pattern of signal hits looks like random noise. No wave, no particle, just quantum chaos. Only when you sort the data into subsets based on the fate of the idler photons does the hidden interference re-emerge like a shy guest, finally revealing a beautiful smile. In plain terms, the experiment tells us that it is meaningless to speak of a photon's behavior, wave or particle, until we specify the entire experimental arrangement, including future measurements. Quantum mechanics does not assign a definite history to the photon independent of our choices. It is not that the photon literally jumps back in time to change its past. Rather, the concept of past itself is intimately entwined with the whole measurement context. It is a lesson in humility. Reality is not a fixed novel, but a choose-your-own-adventure story, and each measurement is a new chapter that retroactively defines what happened before. Perhaps the gentlest way to appreciate this paradox is to imagine a shy guest at a party who refuses to pick a costume until the party is already over. Only when the host films the shindig and shows the video does the guest quietly put on the cape and mask, and only because the host said they would show it to the queen. Until the screening, the partygoers had no evidence the guest ever wore a costume. The guest's costume choice, though made after the fact, reshapes the narrative of the entire evening. Let us not lose sight of the bigger picture. The delayed choice quantum eraser is not merely a trick for attention-seeking photons. It is emblematic of quantum mechanics' core lesson, that the properties of quantum systems are not predetermined, but are co-created by the act of measurement. The measurement context extends not only forward, but in a certain sense backward in how we assign meaning to events. It highlights the deep relationship between information, observation, and reality itself, a theme that echoes through the black hole information paradox, the measurement problem, and every twitch of the quantum wave function that resists neat classification. Of course, one might protest, "This is absurd. Surely events must have an objective history." And yet, experiments confirm Wheeler's prediction over and over.
Photons and atoms play by the rules of quantum mechanics, not by the rules of classical intuition. They do not really care if we think it is absurd. They just follow the mathematics, like perfectly obedient little quantum bureaucrats, stamping wave or particle on our tickets only when we hand them over at the counter. The delayed choice quantum eraser also invites us to ponder the role of information. In these experiments, information is king. If you know which path was taken, you kill the interference. If you erase that knowledge, even in principle, you resurrect the interference, as if by magic. Information, it turns out, is not just an abstract ledger in a cosmic filing cabinet. It is a physical currency that shapes reality itself. So what have we learned as we drift back toward wakefulness?
We have learned that quantum mechanics refuses to let us pin down a photon's past independent of future observations. We have learned that reality, at its tiniest scales, is a tapestry woven from the threads of measurement and information. We have learned that a photon might remain ambivalent, like a guest who refuses to choose a costume until the credits roll. And we have learned that, despite the paradox, the universe keeps ticking along without collapsing into chaos. This paradox is not a puzzle to be solved, but an invitation to marvel. It reminds us that science is not just a body of facts, but a way of seeing, a method for coaxing secrets out of nature's reluctant mouth. And if that is not enough to reframe your understanding of time, causality, and the wily ways of photons, then perhaps nothing will. As you open your eyes and greet the real world again, spare a thought for those photons flipping wave-particle roles like a stand-up comedian, ad-libbing in a cosmic club. And remember, if reality is stranger than fiction, then fiction is just reality without the measurement apparatus. So pay close attention or you might miss the punchline. The Superdeterminism Paradox, when the universe plays chess and cheats. Imagine, if you will, that you are sitting comfortably, ready to explore another deliciously confusing corner of reality. The lights are low, the air is still, and your mind gently whispers, what if everything you ever did, thought, or chose was already determined? Including the decision to ponder that question? Welcome to the Superdeterminism Paradox, where free will takes a coffee break and the universe is accused of playing the longest, most rigged game of chess ever invented. Let us start with a reminder of the most famous quantum oddity, entanglement. Two particles, once linked, seem to communicate instantaneously across vast distances, as if texting each other with cosmic cell service. You measure the spin of one particle and the other instantly knows what to be, even light years away. This phenomenon, which Einstein famously called spooky action at a distance, poked an elegant hole in classical physics and set up the perfect stage for quantum weirdness. In the 1960s, physicist John Bell came along and offered a way to test whether entangled particles truly defy local realism. Bell's theorem showed that if hidden variables predetermined the results, certain inequalities must hold. Countless experiments since then have violated Bell's inequalities, strongly suggesting that either locality, no faster than light communication, or realism, particles have definite properties before measurement, must go. Most physicists chose to sacrifice locality and live with entanglement's eerie reach. But wait, a soft voice whispers again. What if there is a third option? Enter superdeterminism, a concept so bold that even Schrödinger's cat would politely decline to discuss it over dinner. Superdeterminism suggests that the particles in the experimental setup, including the experimenter's so-called free choices, are all correlated because the universe is completely deterministic. The apparent randomness is an illusion. The decision to measure spin in a particular direction, the angle of your detector, even the fact that you are reading these words right now, were all predetermined by the initial conditions of the cosmos at the moment of the Big Bang. If you are feeling a bit trapped, you are not alone. Superdeterminism feels like finding out life is a movie, but the director, script, actors, and even the audience were all programmed from the start. There are no plot twists, no improvisation, no ad-libs. You thought you picked that flavor of ice cream today. The particles of your brain and the molecules of the ice cream shop were already locked into that outcome 13.8 billion years ago. The paradox emerges because superdeterminism would undermine the statistical assumptions of Bell's theorem. It would mean that all the experiments proving quantum randomness were only appearing random because the experimenters themselves were secretly, but inevitably, part of the cosmic script. It is the universe winking and saying, "You thought you had a choice. Adorable." Of course, this is not just philosophical mischief. Superdeterminism proposes that the entangled particles did not communicate at all. Instead, both the particles and the measuring devices were so deeply correlated by the universe's initial state that the outcomes merely matched, no faster-than-light messaging required. You are playing with a deck of cards where every shuffle, every deal, every decision to even play was already fixed at the start. Naturally, this idea sends shivers down the spines of physicists and philosophers alike. If superdeterminism were true, then every scientific experiment ever done was just an elaborate puppet show, with both the puppet and the puppeteer tied to the same invisible strings. This raises unsettling questions about free will. Are we autonomous beings making independent choices, or are we just well-dressed robots following a cosmic to-do list? If every action was predetermined, does responsibility exist? Can you be blamed for eating that third cookie, or was the universe always going to have you eat it? The scientific community generally treats superdeterminism with suspicion, not because it is logically impossible, but because it feels like the ultimate escape hatch. It conveniently explains away every result, while offering no testable predictions. Physics thrives on experiments, and if a theory tells you there is no way to experiment your way out of this box because the box is you, it tends to get an awkward silence at the research conference. Yet a few brave physicists keep exploring it. They argue that dismissing superdeterminism just because it makes us uncomfortable is unscientific. After all, history is full of ideas that were once mocked and later embraced. Quantum mechanics itself was once laughed out of the room before becoming the rock star of modern physics. Superdeterminism, if somehow proven or integrated into a larger framework, could offer a radical unification of physics. It could tie quantum uncertainty to cosmic determinism in a way that avoids faster-than-light signals or multiple parallel worlds. In this vision, the universe would be a single, self-consistent, mathematically perfect machine. Every particle, every decision, every breath already mapped from beginning to end. But then comes the twist, the paradox within the paradox. If you choose to believe in superdeterminism, was that belief predetermined? Could you even choose not to believe it? The mental gymnastics required are enough to make your brain quietly excuse itself for a glass of water. As with so many great paradoxes, the Superdeterminism Paradox offers no resolution, only an exquisite discomfort. It stands as a reminder that the universe does not exist to comfort our sense of fairness. Reality might be rigged from the start, and we are just along for the ride. Yet even in that bleak scenario, there is an odd comfort. If everything was meant to happen exactly this way, then every triumph, every mistake, every heartbreak, and every joy was uniquely yours to experience. The universe may have written the script, but you are still the one living the story. So as you roll over and pull up the blanket of existential uncertainty, remember this. The next time you lose a game of chess, you can always claim superdeterminism made you move that rook. Just be prepared when your opponent leans back and says, "Funny, that is exactly what I was going to say." The uncertainty of quantum vacuum fluctuations, paradox. When nothing refuses to be nothing. You are lying in bed, your eyes slowly adjusting to the soft darkness. The world around you is calm. The cat is asleep. The clock ticks softly. You are convinced there is nothing happening in the room. And then, like an uninvited thought sneaking in through the back door of your mind, the question appears, is nothing really nothing? Welcome to the uncertainty of quantum vacuum fluctuations paradox, where empty space turns out to be the most restless party guest of all. To most of us, a vacuum sounds simple. It is nothing. Zero, an empty glass, a suitcase with no socks. But if you ask a quantum physicist about empty space, you might want to grab a pillow, because the answer is going to keep you awake. In quantum physics, even the vacuum is not truly empty. It bubbles, it jitters, it flickers with possibilities. It is as if the universe itself cannot stand silence and insists on humming quietly to itself. The idea begins with Heisenberg's uncertainty principle. In simple bedtime terms, nature refuses to let certain things be known at the same time with absolute precision. You can know where something is or how fast it is going, but not both. This rule does not only apply to particles zooming around like hyperactive toddlers, it applies to energy itself. Even in a vacuum, where there are no particles, uncertainty demands that energy must fluctuate. The result? What looks like nothing is actually a restless sea of virtual particles popping in and out of existence faster than you can say, "Please let me sleep." These ghostly particles are called virtual because they never hang around long enough to be properly invited into the real particle club. They flicker into existence as particle-antiparticle pairs and then immediately annihilate each other, disappearing as if nothing ever happened. The whole event is over so quickly that nature does not even send a bill. It is a little like a very exclusive party, where two guests sneak in, dance for the briefest moment, then vanish before anyone notices. The bouncer is left confused, holding a guest list with two names that seem to have never existed. But despite their shy appearances, these quantum vacuum fluctuations are very real in their effects. You might ask, if these particles are so fleeting, how do we know they are there? Enter the famous Casimir effect. Place two uncharged metal plates extremely close together in a vacuum and, strangely, they will be gently pushed toward each other. It is as though the vacuum is giving them a soft cosmic hug. What causes this? The fluctuating virtual particles outside the plates create a slightly greater pressure than the limited fluctuation modes between the plates, nudging them together. Scientists have measured this, and it is one of the most beautiful reminders that the universe loves to surprise us with weirdness. The paradox deepens when we realize that these vacuum fluctuations may not be just a curious footnote of physics, but could actually shape the entire cosmos. Cosmologists believe that fluctuations in the early quantum vacuum gave rise to the tiny variations in energy density that ultimately became galaxies, stars, and planets. Yes, every swirling galaxy and glittering star you have ever admired may owe its existence to the jittery chaos of nothingness. It is as if the universe baked a cosmic cake, and the recipe started with one main ingredient, vacuum that could not sit still. This is where the paradox makes itself at home in our imagination. How can something come from nothing? How can empty space have energy? If space is full of virtual particles, is it even empty? If you feel a headache coming on, that is completely normal. Physicists have wrestled with this. Some argue that vacuum energy is the lowest possible energy state of space, a baseline hum that never fully switches off. It is like a cosmic refrigerator that always vibrates no matter how often you tell it to be quiet at night. Others propose that the quantum vacuum is like a field of potential, filled with possibilities that only occasionally manifest in brief flashes before fading back into invisibility. This jittery vacuum also ties directly into the biggest unsolved puzzle in physics, the cosmological constant problem. When physicists calculate the energy of the quantum vacuum, they get an answer so large that if it were true, the universe would have blown itself apart faster than you could blink. Fortunately for us, reality disagrees. The actual observed value is tiny, leading to one of the biggest mismatches between theory and observation in all of science. It is as if you expected to find an elephant in your living room and instead found a dust bunny politely minding its own business. This huge discrepancy leaves scientists staring at their equations in horror, muttering the scientific equivalent of, "Well, that cannot be right." No one knows why the quantum vacuum energy and the observed vacuum energy of the universe differ by such a ridiculous factor. Some say there must be new physics waiting to be discovered. Others shrug and suggest that maybe the universe is just being difficult. So we return to our sleepless question. What is the vacuum? Is it truly nothing, or is it a frothing sea of restless almost somethings? The answer is that in quantum mechanics, nothingness itself is a dynamic player. Even when the stage looks empty, the actors are waiting in the wings, rehearsing for a performance that will never happen. You might wonder what this means for your daily life. Truthfully, unless you are building a particle accelerator in your garage, in which case please check your homeowner's insurance, you will not encounter these vacuum fluctuations directly, but their presence underpins much of modern physics. They influence atomic transitions, particle behavior, and even the stability of the universe itself. There is a certain comfort in knowing that even when life feels empty, there is always something happening beneath the surface. Nothingness is never truly still. It twitches, it wriggles, it dances unseen. The quantum vacuum teaches us that the universe, even at its quietest, cannot resist a little mischief. As you pull the blanket closer and your thoughts gently drift, consider this final reflection. Next time someone tells you they are doing nothing, remember that even the vacuum cannot manage that. And if you happen to hear a faint pop or fizz in the silence of your bedroom, do not worry. It is probably just the quantum vacuum throwing another wild, invisible party. You were never invited, but then again, neither was anyone else. The paradox of unobservable universes. The cosmic hide-and-seek champion. There are times when you gaze up at the night sky and feel small. The stars sparkle with indifference, scattered across the canvas of space. Your thoughts wander, and then, like an unexpected knock at the door, a strange idea arrives. What if there are other universes out there? Universes I can never see, visit, or even prove exist. Congratulations. You have just stumbled into the paradox of unobservable universes, where the cosmic game of hide-and-seek might be played forever, with no hope of tagging it. To start this journey, let us think about what we call the universe. You probably imagine everything that exists: stars, planets, gas clouds, dark matter, and that one mysterious sock that vanished in the laundry. But modern cosmology whispers a more unsettling possibility. What if our universe is only a small patch of a much larger reality? What if countless other universes float out there, separated from us not by distance, but by the very laws of physics that make our existence possible? This is the concept of the multiverse. It comes in many flavors.
Some versions suggest there are infinite bubble universes, each with its own physical constants. In one universe, gravity might be stronger. In another, atoms might never have formed. In yet another, ducks might rule the earth. The possibilities are endless and wonderfully bizarre. Our own universe would be just one bubble adrift in a cosmic bubble bath.
It all sounds exciting until the paradox walks in, calmly sipping a cup of tea. Here it is. By definition, if these other universes are truly separate from ours, they cannot interact with us in any measurable way. No signals, no visits, no postcards. They are completely and forever unobservable. So how can science even talk about them? Science, after all, loves evidence. It adores experiments. It thrives on testable predictions. The unobservable universes offer none of these. They taunt us from behind an impenetrable cosmic curtain. Some theories, such as inflationary cosmology, flirt dangerously close to the multiverse idea. The theory of inflation proposes that a tiny fraction of a second after the Big Bang, space itself expanded faster than light. Some regions stopped inflating and formed normal universes like ours, while other regions kept expanding and formed more universes. Picture a loaf of raisin bread expanding in the oven, except each raisin becomes a separate universe. Now you are hungry and confused at the same time. The trouble is that these universes remain outside our cosmic horizon. The speed of light limits what we can observe. Even with the biggest telescopes imaginable, we can only see as far as light has traveled since the Big Bang. Beyond that, total mystery. Scientists call it the observable universe. Everything else, if it exists, is like a neighbor's house you can never visit, never peek into, and never even confirm is there. This is where the paradox sharpens. The idea of unobservable universes feels both inevitable and meaningless. If they exist but cannot ever be detected, do they really exist at all? It is like claiming to own an invisible pet unicorn. You might insist it is real. You might even name it Sir Nays-a-Lot. But no one can ever prove or disprove that it shares your living room. Some physicists argue that the multiverse is a natural consequence of the mathematics. If the equations point toward multiple universes, who are we to argue? Others protest that without testability, the multiverse remains philosophy, not science. It turns physics into speculative storytelling, which is wonderful for late-night conversations, but terrible for publishing research papers. Then there is the anthropic principle, which sneaks into the discussion wearing a philosopher's robe. It says, maybe we should not be surprised to find ourselves in a universe where conditions allow life, because if they did not, we would not be here to ask the question. In other words, we live in a universe that looks just right for life, because only universes like this one would ever have someone standing under the stars wondering why. This reasoning sounds clever, but it feels suspiciously like cosmic circular logic. It is like saying the chair exists because you are sitting on it. The anthropic principle explains why the universe seems finely tuned for life, but offers no hint about whether other universes exist at all. The paradox of unobservable universes also raises a peculiar question about what it means for something to be real. Is reality defined by what we can observe? Or does reality include everything that could possibly exist, even if we can never reach it? The debate rages on quietly in lecture halls, papers, and minds that cannot resist peeking behind the forbidden curtain. Despite the frustrating lack of evidence, some researchers continue to build models that predict a multiverse. They study patterns in the cosmic microwave background, hoping to find a faint imprint left by a collision with another universe. So far, no such evidence has appeared. If it ever does, it would be like discovering footprints from a neighbor who was never supposed to exist. Until then, the paradox of unobservable universes remains one of the gentlest yet most maddening mysteries of cosmology. It teaches us humility. We may never know whether the cosmic stage extends far beyond our little patch of spotlight. We may forever remain the tiny goldfish, peering through the glass of our aquarium, wondering if other tanks exist just out of sight. Still, there is beauty in the not knowing. The idea that other universes may exist, completely inaccessible and unimaginably strange, reminds us that reality may be far bigger and more diverse than our minds can grasp. It leaves room for wonder, for speculation, and for the sheer joy of thinking about things that may forever remain just beyond reach. As you tuck yourself deeper into bed, staring into the soft darkness, think of the universes that might be floating out there. Some with stars that sing instead of burn. Some where humans never evolved. Some where someone just like you is lying in bed, wondering about you. And then smile, because if you ever lose your keys again, you will have the perfect excuse. You can always claim they slipped into a parallel universe. Try explaining that to the locksmith. The cosmological constant paradox, when empty space weighs a ton. Tonight, you settle into your pillow, convinced that gravity is the only invisible hand tugging at your life. The walls are still, the air is calm, and you whisper to yourself, why is the universe's expansion accelerating when gravity ought to slow everything down? Welcome to the cosmological constant paradox, where empty space itself seems to have energy, and somehow pushes galaxies apart as if it had muscles. Let us begin with a glance at history. In the early 20th century, Albert Einstein formulated his general theory of relativity, a majestic framework describing how matter tells spacetime how to curve, and spacetime tells matter how to move. Einstein's equations predicted a dynamic universe, either expanding or contracting. At that time, prevailing opinion held that the cosmos was static, eternal, unchanging. To keep his equations in harmony with the static universe idea, Einstein introduced a fudge factor known as the cosmological constant, represented by the Greek letter lambda, L. This constant acted like an invisible repulsive force, counterbalancing gravity's pull and holding the universe in place. As it happened, Edwin Hubble's observations in the 1920s revealed that the universe is indeed expanding. Galaxies appeared to drift away from each other. Their light shifted toward the red end of the spectrum, a phenomenon now called redshift. Einstein famously called the cosmological constant his greatest blunder and discarded it, preferring a simpler, zero lambda universe that would expand under its own momentum. Fast forward to the late 1990s. Two independent teams of astronomers observed distant supernovae, exploding stars used as standard candles to measure cosmic distances, and made a startling discovery. Rather than slowing down, the expansion of the universe was accelerating. The galaxies were not merely coasting outward, they were being pushed apart by an unseen force. Out of the dust of history rose Einstein's discarded lambda, resurrected as the leading candidate to explain this cosmic acceleration. The mysterious energy causing this acceleration earned the name dark energy, and it now seems to account for about 70% of the universe's total energy budget. Here we arrive at the paradox. In quantum field theory, empty space is not truly empty. It is a seething froth of virtual particles popping in and out of existence. Quantum vacuum fluctuations. Each fluctuation contributes a tiny amount of energy. If one sums up the contributions of all possible fluctuations, the resulting vacuum energy density predicted by theory is enormous. Physicists calculate a value that is something like 10 or 120 times larger than the observed value inferred from cosmological measurements. That is not a mere disagreement. That is a blow-your-mind mismatch of unimaginable scale. Imagine preparing a cup of coffee, expecting it to hold 10 milliliters, and instead finding it overflowing 1 trillion galaxies in volume. This absurd discrepancy between theory and observation is the heart of the cosmological constant paradox. Why does empty space have energy? And why is that energy so incredibly tiny, yet sufficient to accelerate the expansion of the cosmos? Some scientists propose that there must be an unknown mechanism that cancels out almost all of the vacuum energy, leaving behind the faint residual we observe as dark energy. Others suggest that our understanding of gravity might break down on the largest scales, requiring modifications to general relativity. It is as if one built a ship expecting it to float, but found it sinking unless a nearly perfect balance of counterweights were added in secret compartments. To complicate matters further, the cosmological constant is mathematically equivalent to a constant energy density per unit volume of space. As the universe expands, the energy density remains constant, causing more dark energy to be created from empty space. It is a bizarre property. The more space stretches, the more of this repulsive energy appears, fueling yet more expansion. Picture a loaf of raisin bread where adding dough magically creates more brewer's yeast out of thin air, making the loaf expand faster and faster. Bakers would be baffled. Cosmologists are intrigued. This leads to unsettling philosophical questions. If dark energy dominates the universe, will the expansion eventually tear galaxies, stars, planets, and even atoms apart? In the so-called Big Rip scenario, the repulsive force grows so strong that bound systems disintegrate one by one. First, clusters of galaxies drift irreversibly apart. Then galaxies lose their stars. Then solar systems unravel. Ultimately, atoms themselves could be torn asunder. The timeline for this cosmic endgame depends on the precise value of the cosmological constant, but current estimates place the finale trillions of years from now, well beyond the lifespan of any human civilization. Alternatively, if dark energy remains constant and does not grow stronger, the universe will continue to expand at an accelerating rate, leading to a cold, empty future, often called the heat death. Stars will burn out, black holes will evaporate, and the cosmos will settle into a quiet, frigid expanse with only faint background radiation as testimony to its once vibrant past. Yet another possibility arises if dark energy slowly decays over time. In some models, the cosmological constant might not be constant after all, but a dynamic field, quintessence, that changes with cosmic time. In this scenario, dark energy's strength could diminish, allowing gravity to reclaim dominance and perhaps even trigger a contraction phase. The universe might oscillate through cycles of expansion and contraction, an eternal cosmic heartbeat. Throughout all these speculations, the central question remains unresolved. What is the true nature of dark energy? Is it vacuum energy, an intrinsic property of spacetime? Is it a scalar field slowly rolling down a potential energy hill? Or is it an artifact of our incomplete understanding of gravity at immense distances? Researchers hunt for clues in the cosmic microwave background, the faint afterglow of the Big Bang, and in large-scale surveys mapping the distribution of galaxies. They search for subtle imprints of dark energy's influence on the formation of cosmic structures, on the bending of light by gravity, gravitational lensing, and on the clustering of galaxy clusters. Upcoming observatories, both ground-based and orbital, aim to measure dark energy properties with unprecedented precision. In the meantime, theorists continue to wrestle with the vacuum catastrophe, the appalling mismatch between quantum predictions and cosmological observations. Some propose that a multiverse might hold the answer. Perhaps different regions of a vast cosmic landscape have different values of the cosmological constant, and we find ourselves in one of the rare pockets where the constant is small enough to allow galaxies, stars, planets, and life to form. In other words, the anthropic principle rescues us by saying, we observe a small cosmological constant because if it were not small, we would not be here to observe anything. While this line of thinking unsettles many, it nevertheless highlights one of the profound lessons of modern cosmology, that fundamental constants may not be universal after all, and that our very existence might be tied to a delicate balance of cosmic parameters. As your eyelids grow heavy, reflect upon the strange reality that empty space is neither empty nor inert. It carries energy that accelerates galaxies across cosmic voids. It may determine the ultimate fate of all that exists. And yet, the true value of that energy remains one of the greatest unsolved mysteries in physics, the cosmological constant paradox. So as you drift towards sleep, consider this final thought. If empty space really does weigh on the universe so heavily, perhaps one day we will measure it precisely, solve the paradox, and sail untroubled into a future of cosmic understanding. Or perhaps the answer is hiding so deeply that even the universe's own acceleration cannot reveal it. In either case, the cosmos retains its sense of humor, reminding us that sometimes the emptiest things are the most profoundly puzzling, and that the best punchlines begin with a question no scientist can fully answer, at least until after coffee. The memory erasure paradox, when forgetting becomes a puzzle. You wake up slowly, stretch under the weight of your blanket, and glance around the quiet room. Everything looks normal. But then, like a rogue whisper, a peculiar thought sneaks into your mind. If a memory is erased so completely that I cannot recall it, did it ever really exist? Welcome to the memory erasure paradox, where the boundaries between existence and non-existence blur in the most personal and mysterious way possible. At first glance, memory seems simple. You experience something, your brain records it, and you retrieve it later like pulling a favorite sweater from a drawer. But anyone who has ever walked into a room and forgotten why they went there knows it is not that straightforward. Memory is delicate. It fades, distorts, rewrites itself, and sometimes vanishes altogether. The memory erasure paradox takes this everyday frustration and pushes it to its philosophical and scientific limits. Let us start with a human example. Imagine you have a memory of a childhood event, a vivid image of playing in the park under a bright blue sky. Now imagine a technology or condition that could erase that memory so completely that no trace remains. The question then becomes, was that memory ever part of your life if it cannot be accessed or recalled? Does an experience exist only if you can remember it? This paradox stretches beyond forgetful afternoons and lost car keys. It touches the heart of what we think of as identity. Our memories form the narrative we tell ourselves about who we are. Without them, the storyline becomes fragmented or even blank. If the memory of an event disappears entirely, has the event itself been deleted from the fabric of your personal history? Science fiction has long toyed with this unsettling possibility. Films, books, and shows have imagined memory-erasing devices ranging from gentle neural dampeners to terrifying brain wipes. But real-world science has uncovered phenomena that feel eerily close. Conditions like amnesia, Alzheimer's disease, or even traumatic brain injuries can erase memories so thoroughly that a person no longer recognizes familiar faces, places, or even their own reflection. The paradox deepens when we consider whether a memory is ever truly gone. Neuroscience suggests that memories may never be fully deleted, only disconnected. They may linger like ghosts in the circuitry of the brain, inaccessible but not entirely absent. Studies in animals have shown that under certain conditions, supposedly lost memories can be recovered by stimulating specific neurons. It is as if the memory was hidden behind a locked door, and science just has not found all the keys yet. So, is an erased memory erased in the truest sense? Or does it simply retreat into the shadows, waiting for the right combination of events to reappear? The memory erasure paradox sits quietly between these possibilities, smiling enigmatically. Another twist comes from the idea of false memories. Sometimes our brains fabricate events that never happened. A person may confidently recall a conversation, an encounter, or an entire day that, according to all available evidence, never took place. This raises a curious question. Which is more real? A memory that once existed and was erased, or a memory that never existed but feels perfectly real? The paradox invites you to ponder whether memory is about truth or simply about belief. In quantum mechanics, information has an almost sacred status. The principle of information conservation suggests that information cannot be destroyed. Even when matter falls into a black hole, modern theories argue that the information must be somehow preserved, even if it seems forever out of reach. Some physicists have playfully suggested that the brain, as a physical system, might follow a similar rule. Could it be that memories, like quantum information, never truly vanish, but are encoded in ways we do not yet understand? Philosophy, as always, steps into the conversation with thoughtful questions. The classic thought experiment asks, if a person had every memory of a certain period erased, are they still the same person? Is continuity of memory required for continuity of identity? Or is there a core self that remains even when the pages of life's story are blank? These are not just theoretical questions. Modern legal systems wrestle with memory all the time. Eyewitness testimony is notoriously unreliable. People forget details, blend events together, or unintentionally invent new facts. Courts are increasingly aware that memory is not a perfect video recorder, but a fragile, ever-changing story subject to countless edits. The paradox also touches the realm of future ethics. As technology advances, scientists are beginning to explore ways to dampen traumatic memories for those suffering from post-traumatic stress disorder. The hope is to ease suffering by blurring the emotional intensity of painful recollections. But critics wonder, if you erase the memory of a trauma, do you erase a piece of what made a person who they are? Can healing come at the cost of identity? This debate hints at a fascinating, yet frightening possibility. Could someone use memory erasure intentionally, sculpting their mind to forget things they regret? Could we one day choose to forget heartbreak, failure, embarrassment? Would the ability to edit life's painful chapters make us happier, or leave us hollow and incomplete? Even sleep plays a role in the memory erasure paradox. Every night, our brains perform a strange dance of memory reinforcement and memory pruning. Some memories are strengthened, while others are quietly deleted to free up space for new experiences. We never know which moments will be preserved and which will be swept away like footprints in the sand at high tide. The mystery is that you cannot mourn a memory you no longer remember having. As you reflect on this, the memory erasure paradox offers no tidy solution. It reminds us that memory, like time, is both real and elusive, present and absent, reliable and deceptive. Whether forgotten by accident, erased by trauma, or removed by future technologies, the very act of forgetting invites us to consider what truly defines experience and identity. The paradox gently nudges us to treasure our memories while we have them, knowing that they are as fragile as mist on a cold morning. The laughter shared with a friend, the sound of rain on a window, the warmth of a long-forgotten summer afternoon, all become part of the mosaic that makes up a life. And yet, any of these could slip quietly into the void, leaving behind only a sense that something precious once was there. So as you pull the blanket a little tighter, and prepare to surrender to sleep's forgetful embrace, consider this one final thought. If forgetting is unavoidable, at least you will not remember what you forgot, which, when you think about it, might be the only truly foolproof memory protection plan ever invented. The Unruh effect paradox. When moving fast makes empty space hot, you are comfortably settled, perhaps with a cup of tea in hand, enjoying the stillness of the evening. The world feels predictable. A chair is a chair. Empty space is cold and empty. But then, like a mischievous breeze sneaking through a crack in the window, a peculiar idea drifts into your thoughts. Can the temperature of empty space depend on how fast I am moving? Welcome to the Unruh effect paradox, where motion itself decides whether you feel the warmth or chill of the universe. In most everyday experiences, temperature is straightforward. If you sit by a fire, you feel warm. If you stand outside in winter, you feel cold. But physics, with its fondness for complicating the obvious, suggests that temperature might not be quite so simple after all. In the 1970s, physicist William Unruh proposed a startling theoretical prediction. According to the principles of quantum field theory and Einstein's relativity, an observer at rest in empty space experiences a vacuum, no particles, no heat, no fuss. But if that same observer were to accelerate uniformly, even in perfect emptiness, they would perceive the vacuum as a warm bath of particles. This phenomenon is known as the Unruh effect. At first glance, this sounds utterly ridiculous. How can empty space be cold for one person and hot for another? Is the universe playing favorites? The key lies in the very fabric of reality. In quantum field theory, the vacuum is not empty but filled with fluctuating fields. These fields exist everywhere, but whether or not they appear as particles depends on how an observer moves through them. A person at rest glides smoothly across the sea of fluctuations and sees only stillness. An accelerating observer, however, churns up these fluctuations, much like a swimmer disturbing the calm surface of a lake. The result? Particles appear where none existed before. The faster you accelerate, the hotter the apparent temperature becomes. It is as though the universe rewards you for your effort with an unwanted and imaginary sauna experience. Of course, the Unruh effect is tiny. In everyday situations, even rapid accelerations produce temperatures so low that no thermometer could detect them. A space shuttle launch would only raise the perceived temperature by a fraction of a degree above absolute zero. To experience the Unruh effect at room temperature, you would have to accelerate at mind-bending rates no human or machine can currently achieve. Think of it as the world's most impractical heating system. The paradox lies not in the inconvenience, but in the philosophical implications. Temperature, which we think of as an objective property, becomes a matter of perspective. It challenges the very notion of reality. What does it mean for something to be hot if two observers standing side by side, one stationary, one accelerating, disagree about the temperature of the same space? This is where relativity meets quantum mechanics in a subtle, mind-bending handshake. According to relativity, motion is relative. There is no universal state of rest or motion. What matters is how you are moving relative to something else. The Unruh effect suggests that even the vacuum plays along, shifting from serene to sizzling depending on your path through space-time. Some physicists connect the Unruh effect to another profound phenomenon, Hawking radiation. In the 1970s, Stephen Hawking showed that black holes are not entirely black. They emit faint radiation due to quantum effects at the event horizon. Interestingly, the mathematics behind Hawking radiation and the Unruh effect are remarkably similar. Both arise from the strange relationship between acceleration, horizons, and quantum fields. In the case of a black hole, the horizon is the boundary beyond which nothing escapes. For the Unruh effect, the accelerating observer experiences a kind of personal horizon, the point beyond which signals can no longer catch up. To the observer, it seems as though particles are being emitted from this invisible barrier. The paradox deepens because there is no physical boundary in empty space. The the horizon is an illusion caused purely by acceleration. It exists only for the observer, not for anyone else. The universe remains indifferent, yet it behaves as though it cares very much about how quickly you are moving. Philosophers and physicists alike marvel at what this means for the nature of observation. Reality itself becomes a deeply personal experience. Two observers can exist in the same location and completely disagree on what is happening, with both being technically correct. It is the ultimate cosmic agree to disagree. So far, the Unruh effect remains a theoretical prediction. No direct experimental confirmation exists, mainly because of the extreme conditions required, but indirect evidence and consistency with other tested theories lend it credibility. Scientists continue to explore clever ways to detect the effect, perhaps using ultra-powerful particle accelerators or analog systems that mimic the behavior of quantum fields under acceleration. Even if unproven, the Unruh effect serves as a powerful reminder that nature rarely fits neatly into human expectations. It blurs the boundaries between emptiness and somethingness, between motion and stillness, between hot and cold. It whispers to us that even the vacuum is not what it seems, that behind the apparent silence of space lies a hidden symphony of possibilities. For those who find this unsettling, take comfort in knowing that your living room remains at one temperature, no matter how quickly you run from the couch to the fridge. You will not accidentally heat up your kitchen by sprinting to grab a snack. The Unruh effect stays mercifully out of reach for now. As your eyelids grow heavier and the mysteries of the universe swirl gently in your thoughts, consider this parting reflection. Perhaps reality itself is like the most patient trickster, always behaving well when you stare at it calmly, but ready to surprise you the moment you start to accelerate. And if you ever feel unexpectedly warm while sitting completely still, do not blame physics. Blame the cat sleeping on your lap. The black hole information paradox. When the universe forgets your secrets, a flicker of curiosity crosses your mind. Imagine plunging your most precious memories into a black hole and wondering if you will ever see them again. Welcome to the black hole information paradox, where the universe behaves like a cosmic shredder, threatening to erase every secret you ever held dear. Black holes are regions of space so dense that nothing, not even light, can escape once it passes the event horizon. According to Einstein's general relativity, a black hole is defined entirely by three properties: its mass, its charge, and its spin. All other details about the matter that formed the black hole, every particle, every bit of information, appear to vanish. This led early physicists to conclude that black holes destroy information, leaving only a bald exterior description. But quantum mechanics insists on the opposite. In the quantum world, information is sacred. The principle of unitarity in quantum theory holds that information about a closed system's initial state can always be recovered from its final state. In simpler terms, if you know the quantum state of a system now, you can, in principle, reverse time and reconstruct its past. Information cannot be created or destroyed. It can only transform. This fundamental tension between general relativity and quantum mechanics gave rise to the black hole information paradox. If information truly disappears inside a black hole, then quantum mechanics is violated. If information is preserved, then our understanding of black holes via general relativity must be wrong in a profound way. In the 1970s, Stephen Hawking discovered that black holes are not completely black. They emit a faint glow, known today as Hawking radiation, arising from quantum effects near the event horizon. Particle-antiparticle pairs pop into existence just outside the horizon. One falls in, the other escapes as radiation. Over eons, this process causes a black hole to lose mass and eventually evaporate entirely. Hawking's calculation indicated that this radiation is purely thermal. It carries no information about what fell into the black hole. If a black hole evaporates completely, what remains is only thermal radiation, uniform and featureless, devoid of any imprint of the original matter. Information seems to have been lost forever in the singularity, the point at the black hole's core where densities become infinite and known physics breaks down. This is where the paradox tightens its grip. On the one hand, general relativity predicts information loss. On the other hand, quantum mechanics insists on information preservation. The community of theoretical physicists found itself at an impasse. Either accept that quantum mechanics fails on the largest scales, or concede that black holes reveal a deeper layer of reality beyond classical gravity. Over the decades, numerous proposals have attempted to resolve the paradox. One idea is that information is somehow encoded in subtle correlations within Hawking radiation. Rather than being purely thermal, the radiation might carry hidden quantum entanglements that, when decoded, reveal the black hole's history. This suggests that black hole evaporation is unitary after all, and no information is lost. However, demonstrating exactly how this encoding works remains a formidable challenge. Another bold proposal is the holographic principle. Inspired by string theory and developed by Gerard Hooft and Leonard Susskind, the holographic principle suggests that all information contained in a volume of space can be represented on its boundary surface. In the black hole context, this means that the event horizon acts like a hologram, storing every bit of information about infalling matter in two-dimensional form. The paradox then dissolves. Information is never lost. It is merely transcribed onto the horizon. More recently, ideas such as black hole complementarity and firewall hypotheses have sparked intense debate. Black hole complementarity posits that no single observer ever sees information destroyed. An outside observer sees information encoded in Hawking radiation, while an infalling observer perceives graceful passage through the horizon. Both descriptions are valid but mutually inaccessible, like two sides of a coin viewed separately. The firewall hypothesis, by contrast, suggests that the horizon becomes a searing wall of high-energy quanta that burns up any infalling information, potentially violating relativity but preserving quantum unitarity. A particularly intriguing development comes from the study of quantum gravity in low-dimensional toy models, where explicit calculations indicate that information may gradually leak out through intricate quantum correlations. These models lend hope that a full resolution awaits in a yet-to-be-formulated theory of quantum gravity, where space-time geometry and quantum fields emerge from deeper microscopic building blocks. Beyond the high-level physics, the black hole information paradox touches on profound philosophical questions. What does it mean to know the past of a system if its history can be wiped clean? Does reality exist independently of observation, or is it co-created by the act of measurement? Black holes challenge the notion of objective reality by making information both the currency of physics and the most elusive commodity. In practical terms, astrophysicists are exploring observational signatures that might hint at quantum effects near black hole horizons. Future observatories, such as the Next Generation Event Horizon Telescope, aim to capture images of black hole shadows with unprecedented resolution. While such data may not directly reveal information-preserving mechanisms, they will constrain theoretical models and guide our understanding of black hole thermodynamics and quantum gravity. For now, the black hole information paradox remains one of the deepest puzzles in modern physics, a testament to the tension between gravity and quantum mechanics, and a beacon guiding us toward the ultimate theory of everything. It reminds us that the universe guards its secrets in the shadows of its most extreme objects, inviting us to probe ever deeper. As you drift towards sleep, imagine your personal diary, every thought, every dream, falling past a black hole's event horizon. Does your inner life vanish like dust on the breeze, or is it etched forever in the fabric of space-time? Whether information is lost or saved, the universe still keeps its sense of humor. And if you ever misplace your keys, you can always blame them on your own personal micro-black hole, though you may never get them back. The vacuum energy paradox. When nothingness packs a punch. The morning sun streams gently through your window as you stretch and yawn. All seems calm and ordered. But just as you reach for your first sip of coffee, a troubling thought knocks politely at the back door of your mind. If space is empty, why does it seem to have energy? Welcome to the vacuum energy paradox, where nothingness cannot sit quietly and insists on making itself very much something. At first glance, a vacuum should be simple. It should be the absence of everything, a perfect void, clean, empty space. If you could somehow scoop up a jar of perfect vacuum, you would expect it to weigh nothing, do nothing, and generally mind its own business. But quantum physics, as usual, has other plans. According to quantum field theory, empty space is not really empty. It is a restless sea of invisible activity. The vacuum is filled with quantum fields that fluctuate wildly, even in the absence of matter. These fields create pairs of virtual particles that pop in and out of existence with reckless abandon, borrowing energy from the universe's accounting system and repaying it so quickly that no one seems to notice. You could imagine the vacuum as an endless ballroom where ghostly dancers swirl in and out, appearing for the briefest moment before vanishing into thin air. It looks empty at first glance, but beneath the surface, there is a lively party in full swing. The paradox comes when we try to add up the contributions from all of these fluctuating quantum fields. Theoretically, every possible mode of vibration, every energy level of every field, contributes something to the total vacuum energy. The calculations should give us the energy density of empty space. Here is the problem. When physicists do the math, the predicted value of the vacuum energy is enormous, staggering, ludicrous. The number exceeds the observed value by a factor of about 10 to the power of 120. This is not just a minor error. It is the largest known discrepancy between theory and experiment in all of physics. Imagine ordering a single grain of rice and being delivered a mountain the size of the Milky Way. That is the level of mismatch we are dealing with. The calculated vacuum energy should be enough to blow the universe apart instantly. Galaxies, stars, planets, and even atoms should not exist. And yet here we are, sipping coffee, peacefully ignoring the cosmic contradiction. This mismatch has earned the title of the vacuum energy paradox. Why does the vacuum energy exist at all? Why is it not zero? And most importantly, why is it so unimaginably small compared to theoretical expectations? The connection between vacuum energy and the expansion of the universe lies at the heart of this puzzle. In Einstein's general relativity, energy and pressure determine the curvature of space-time. A non-zero vacuum energy acts as a repulsive force, driving space itself to expand. We call this phenomenon dark energy. Observations show that dark energy makes up about 70% of the universe and is responsible for the accelerating expansion of cosmic space. This leads to a second layer of the paradox. If the vacuum energy is dark energy, why is it just strong enough to affect galaxies, but not strong enough to rip them apart? The vacuum energy must be exquisitely fine-tuned to an absurd degree. There is no known mechanism in particle physics to explain how nature arrived at such a perfect balance. Theories abound. Some physicists believe that an unknown symmetry cancels out most of the vacuum energy. Others propose that the value of the vacuum energy might vary across a vast multiverse, and we happen to live in the rare region where the value is small enough for life to exist. This is called the anthropic principle. It suggests that our universe is not unique, but merely one bubble in a cosmic foam of universes, each with its own laws and constants. The anthropic explanation, while tempting, feels unsatisfying to many scientists. It suggests that there may be no deeper reason why the vacuum energy has the value it does. It just happens to be the case in our cosmic neighborhood. In scientific terms, this feels a bit like throwing up your hands and saying, well, it just is. Other researchers speculate that our current theories are incomplete. They hope that a future theory of quantum gravity, one that fully unites quantum mechanics and general relativity, will explain the smallness of the vacuum energy naturally, without the need for unlikely coincidences. For now, though, the vacuum energy paradox remains unresolved. It is a gentle but constant reminder that our understanding of the universe is still incomplete. The paradox patiently waits, quietly mocking our attempts to explain why something that should dominate everything barely seems to whisper. The strange thing about vacuum energy is that we can measure its effects indirectly. The accelerating expansion of the universe, observed through distant supernovae and the cosmic microwave background, reveals the presence of dark energy. We know it is there. We know its strength. We just do not know what it is. Some experiments have even explored whether the vacuum energy could have local effects, such as in the Casimir effect. Two uncharged metal plates placed extremely close together in a vacuum experience a tiny attractive force due to differences in vacuum fluctuations on either side. This force has been measured and confirms the jittery nature of the vacuum. But it does not explain why the total vacuum energy on cosmic scales remains so low. The vacuum energy paradox forces us to rethink our most basic assumptions about space, time, energy, and reality itself. It teaches us humility. It reminds us that nature often keeps its deepest secrets just out of reach, teasing us with clues, but refusing to give away the full story. Even though this puzzle frustrates physicists, it inspires them too. The quest to understand vacuum energy drives much of modern theoretical physics. It encourages the development of bold new ideas: supersymmetry, string theory, extra dimensions, quantum cosmology. The vacuum energy paradox acts as a lighthouse, guiding researchers through the fog toward the hidden island of ultimate understanding. As you relax under your blanket and let the swirling mysteries of the cosmos lull you toward sleep, consider this final reflection. In the grand ballroom of reality, where even nothingness cannot stay still, the vacuum insists on dancing when no one is watching. And if you ever feel as though your house feels strangely full for no reason at all, do not blame the clutter. Just smile and say, "Ah yes, it must be the vacuum energy again, refusing to take a day off." The Olbers Paradox. Why the night sky is dark in an endless sea of stars. You step outside on a crisp, clear evening and look up. The sky above stretches into deep, velvet darkness, sprinkled with the soft glow of distant stars. It feels peaceful, serene, exactly as it should be. Then, as your thoughts wander, a quiet question sneaks into your mind. If the universe is infinite and filled with stars, why is the night sky not as bright as the sun? Welcome to the Olbers Paradox, the cosmic riddle that gently reminds us the universe may not be as straightforward as it appears. The paradox is named after the German astronomer Heinrich Wilhelm Olbers, who popularized the question in the early 19th century. Yet versions of the puzzle had been raised as far back as the ancient Greeks. The basic idea seems disarmingly simple. Imagine an infinite, static universe filled uniformly with stars. No matter which direction you look, your line of sight should eventually hit a star. The entire night sky should glow brilliantly, as blinding as a cosmic light bulb left on in an otherwise dark room. This is not what we see. The night sky is mostly dark. Even in the clearest, most remote locations, the stars remain distant pinpricks of light. The absence of overwhelming brightness is the heart of Olbers' paradox. Several intuitive explanations fail under closer examination. One might think the dust and gas between stars absorbs light. The problem is that over cosmic timescales, the dust itself would heat up and re-emit the absorbed light, eventually glowing just as brightly. Others suggest that maybe stars simply are too far away. But in an infinite universe, distance becomes irrelevant. Every patch of sky should still be illuminated by countless overlapping sources. The real resolution did not arrive until the development of modern cosmology in the 20th century. The first key insight comes from the realization that the universe is not static, it is expanding. Edwin Hubble's observations in the 1920s showed that distant galaxies are receding from us, and the farther away they are, the faster they move. This stretching of space causes the wavelengths of light to lengthen, shifting visible light into infrared or even microwave regions of the spectrum. This process, known as redshift, dims the light from distant galaxies and prevents the buildup of overwhelming brightness. The second major clue lies in the age of the universe. Our cosmos is not eternal. It began with the Big Bang around 13.8 billion years ago. This means there is a limit to how far we can see, the observable universe. Light from objects farther away than this limit has not had time to reach us. The cosmic horizon creates a natural boundary, reducing the number of stars whose light contributes to our night sky. A third important factor is the finite lifetime of stars. Even in an infinite universe, stars are born, live out their lives, and die. The sky does not glow continuously because not every location is occupied by an active star. There are dark patches where stellar nurseries have yet to ignite, or where stars have already faded into white dwarfs, neutron stars, or black holes. In combination, these effects resolve Olbers' paradox. The night sky remains dark, not because there are no stars, but because of the dynamic, evolving nature of the cosmos. Expansion stretches and dims the light. The age of the universe limits what we can see, and the impermanence of stars prevents uniform illumination. While this may seem like a tidy answer, the paradox lingers as a gentle philosophical reminder. It forces us to confront assumptions about infinity, time, and the very structure of the universe. For much of human history, people assumed the universe was eternal and unchanging. Olbers' paradox subtly hinted that something was deeply wrong with that view, long before telescopes confirmed the expansion of space. The paradox also paved the way for new discoveries. Understanding why the night sky is dark led astronomers to rethink the nature of space, time, and energy. It helped reinforce the idea of a finite, evolving universe, which ultimately pointed toward the Big Bang theory. Interestingly, the night sky is not completely dark. It glows faintly in the microwave range. This is the cosmic microwave background radiation, the afterglow of the Big Bang, stretched and cooled over billions of years. Detected accidentally in 1965 by Arno Penzias and Robert Wilson, this faint hum of energy provides one of the most compelling pieces of evidence for the Big Bang. The cosmic microwave background serves as a quiet backdrop to the night sky's darkness, a faint whisper of the universe's explosive origin. If our eyes could see microwaves, the night would appear anything but black. It would glow with the soft, uniform warmth of that ancient light. Olbers' paradox also inspires creative thought experiments. Imagine a hypothetical universe that did not expand, had existed forever, and had an infinite number of stars with infinite lifetimes. Such a universe would not be dark. The sky would be ablaze in every direction. Life, if it could exist at all, might never have evolved under such relentless brightness. Fortunately for us, we live in a universe where the night sky offers both beauty and mystery. Its darkness allows for peaceful contemplation, for storytelling under the stars, and for the exploration of deep questions about existence. The paradox also invites speculation about the far future. As the universe continues to expand, distant galaxies will move farther away, and their light will eventually slip beyond our cosmic horizon. Trillions of years from now, the night sky may grow even darker. Future astronomers, if any remain, may see only the stars within their local galactic cluster and have no evidence of the broader cosmos. They might wonder, as we did, why the night is so dark. Despite the scientific explanation, the emotional power of Olbers' paradox endures. It captures the strange sensation of standing beneath an infinite sky and wondering why that infinity does not overwhelm us. It encourages humility and awe, reminding us that the universe is not only stranger than we imagine, it is stranger than we can imagine. As you gaze once more at the peaceful blackness speckled with stars, remember that the darkness itself tells a story. It is the silence between cosmic notes, the pause in an endless symphony of creation and destruction. The stars shine because they are finite, distant, and rare, and it is that very scarcity that makes them beautiful. So the next time someone asks why the night sky is not blazing like the surface of a star, you can explain expansion, redshift, cosmic horizons, and stellar lifetimes. Or you can simply smile and say, because the universe knows we would never get any sleep. The paradox of the arrow of time. Why time only marches forward. You wake up to the familiar sound of your alarm, groan, and glance at the clock. Time has moved forward, just as it always does. The coffee that was cold yesterday morning is still cold today. The toothpaste squeezed from the tube does not climb back inside, But as you shuffle into your day, an unsettling thought tiptoes into your mind. If the laws of physics work just as well backward as forward, why does time only seem to flow in one direction? Welcome to the paradox of the arrow of time, where the universe insists on marching to the beat of a one-way drum. At the heart of this paradox lies a contradiction between human experience and physical theory. In everyday life, time feels irreversible. Ice melts but never unmelts. A dropped glass shatters but does not leap back together. We age but do not grow younger. This relentless forward progression is known as the arrow of time. However, the fundamental laws of physics, whether classical Newtonian mechanics, electromagnetism, quantum theory, or even relativity, are time-symmetric. The equations describing the motion of planets, the behavior of atoms, and the interactions of particles work perfectly well if you reverse time. The math does not care whether the movie plays forward or backward. This clash between symmetric laws and asymmetric experience is the essence of the paradox. Why do we live in a universe where time clearly has a preferred direction? The first major clue comes from thermodynamics, specifically the second law of thermodynamics. It states that in an isolated system, entropy tends to increase over time. Entropy is often described as a measure of disorder. A neatly stacked deck of cards has low entropy. A shuffled deck has high entropy. Once the deck is mixed, you will not see it spontaneously rearrange itself. In this view, the arrow of time is the arrow of increasing entropy. The past had lower entropy than the present. The future will have higher entropy still. Our perception of time flowing forward is tied to this steady march toward disorder. Yet this explanation raises more questions than it answers. Why was the universe's entropy so low in the past, particularly at the moment of the Big Bang? The early universe was incredibly hot, dense, and uniform, a state of surprisingly low entropy. Physicists are still searching for the reason behind this peculiar initial condition. Without a deeper understanding, the entropy explanation feels like a partial answer. Another perspective on the arrow of time comes from cosmology. As the universe expands, space itself stretches, providing more room for entropy to increase. Stars form and burn, life evolves and changes, and structures grow ever more complex. This expansion provides a kind of cosmic clock, defining a past and a future. However, this too is not entirely satisfying. Even in an expanding universe governed by reversible laws, why should entropy have started so low? The mystery remains unsolved. In quantum mechanics, the arrow of time appears again in the process of measurement. When a quantum system interacts with the environment, what physicists call decoherence, it loses its delicate superposition of possible states and settles into a definite outcome. Before measurement, a particle exists in a cloud of probabilities. After measurement, it snaps into a single reality. This transition appears irreversible. The universe remembers what happened. The movie only plays one way. Yet the underlying quantum equations are still time-symmetric. The irreversibility seems to emerge only when systems become large enough to interact with their surroundings. The line between reversible micro-events and irreversible macro-events remains blurry. The psychological arrow of time is perhaps the most relatable. We remember the past, but not the future. Our memories are like breadcrumbs scattered along the trail behind us. The connection between memory and thermodynamics may not be coincidental. Storing a memory increases entropy. Erasing it does too. Our minds, like the universe, move from less information to more, from simplicity to complexity. The paradox also invites strange and delightful thought experiments. Imagine living in a universe where time flows backward. You would wake up younger each day. Coffee would pour back into the pot from your cup. Raindrops would leap up from puddles and soar into the clouds. It would be familiar and alien all at once. The arrow of time also poses deep puzzles for black hole physics. As black holes evaporate via Hawking radiation, what happens to the information about the objects that fell in? Does the process respect the arrow of time, or does it introduce an even deeper layer of paradox? Even the possibility of time travel, a favorite topic of science fiction, runs into problems with the arrow of time. Many physicists believe that any time machine capable of traveling backward would violate causality, the rule that effects follow causes. Break that rule and you risk paradoxes like meeting your own grandfather before he meets your grandmother, a scenario that keeps both philosophers and screenwriters awake at night. The arrow of time remains one of the greatest unsolved mysteries of physics. It feels so fundamental, so woven into the fabric of our lives, and yet science cannot fully explain why it exists. We understand how entropy behaves, but not why the universe started in a state of low entropy in the first place. Some researchers speculate that answers may come from theories of quantum gravity or multiverse models. Perhaps our universe is just one of many, each with its own arrow of time, or none at all. Until then, we are left with a riddle that defines our every waking moment, but refuses to reveal its full nature. Despite its mystery, the arrow of time offers a quiet beauty. It allows stories to unfold, music to build to a climax, and life to progress from beginning to end. It provides the backdrop against which change becomes meaningful. So as you prepare to sleep and let time quietly carry you from today to tomorrow, consider this gentle thought. Maybe the reason time flows forward is that if it did not, we would never get to experience the satisfaction of finishing a good meal, the bittersweet beauty of a sunset, or the simple joy of finally getting the toothpaste to squeeze out just right. The Godel Universe Paradox. When time ties itself in a knot, you sit quietly, flipping through the pages of a familiar book. Beginning, middle, and end flow in perfect order, just as every book should. But then a strange idea taps you gently on the shoulder. What if time itself did not have a clear beginning or end? What if time curved around and allowed you to loop back to the past? Welcome to the Godel Universe Paradox, where the story of the cosmos might not be a straight line, but a cosmic circle. In 1949, the brilliant logician and mathematician Kurt Gödel shocked the physics community by offering a mind-bending solution to Einstein's equations of general relativity. While most people know Gödel for his incompleteness theorems in mathematics, few realize that he also dabbled in the deepest mysteries of time itself. His solution described a rotating universe where time could, in theory, loop back on itself. You could travel into your own past along a closed, time-like curve, a path through space and time that bends into a circle. To understand the strange beauty of this idea, picture yourself walking around a circular track. No matter how many laps you complete, you never leave the track. In Gödel's universe, the fabric of space-time itself forms that kind of loop. Start in the present, move forward, and eventually arrive back at the same moment you left, only in the past. Time becomes not a river flowing from source to sea, but more like a carousel, endlessly spinning, always returning. This is where the paradox emerges. If time travel to the past were possible, it seems to invite logical absurdities. You could meet your younger self. Worse, you might accidentally or deliberately change the course of history. The classic example is the grandfather paradox. What happens if you travel back in time and prevent your grandparents from meeting? Would you cease to exist? But if you never existed, who went back in time to interfere? Gödel's universe did not just raise eyebrows, it sent them soaring into orbit. Scientists and philosophers scrambled to understand what this meant for causality, the chain of cause and effect that keeps the universe orderly. If the past can be revisited and altered, the very fabric of reality unravels. Fortunately, or unfortunately depending on your taste for adventure, Gödel's rotating universe does not match what we observe. Our cosmos shows no evidence of the kind of global rotation required by Gödel's solution. The stars and galaxies expand outward, but they do not collectively spin in the way Gödel imagined. Still, the Godel Universe Paradox remains important. It taught physicists that Einstein's equations allow for solutions where time loops are mathematically possible. The laws of physics do not strictly forbid time travel. Whether nature allows such strange behavior in practice is another matter. The idea of closed time-like curves pops up in other theoretical models as well. Wormholes, theoretical tunnels connecting distant points in space-time, might allow travel between different moments if the geometry can be stabilized. Cosmic strings, hypothetical defects in the fabric of space left over from the early universe, could also create closed, time-like curves under the right conditions. These remain purely speculative, but the possibility keeps physicists, philosophers, and science fiction writers awake at night. The paradox also forces us to ask what time really is. Is it a rigid, one-way progression, or is it a flexible, geometric dimension that can be bent and twisted? Einstein's theory treats time as part of space-time, a unified fabric that can be stretched and warped by mass and energy. Godel showed that under certain conditions, time might even fold back on itself. Some physicists argue that even if closed, time-like curves exist mathematically, quantum effects or unknown laws of quantum gravity might intervene to prevent paradoxical scenarios. This concept is sometimes called the chronology protection conjecture, proposed by Stephen Hawking. It is as though the universe has a built-in rule that slams shut the door to the past before anyone can sneak through and cause trouble. Even so, no one can say with certainty whether such protection exists. The Godel universe paradox remains a stubborn puzzle, sitting at the intersection of physics and philosophy. It challenges our most basic assumptions about time, free will, and the nature of reality. The paradox also reveals a curious irony. While Godel's solution permits time travel, it describes a universe with no global sense of time. There is no universal now shared by all observers. Everyone's clock follows its own path, and what feels like the present to you might be someone else's ancient history. It is the ultimate cosmic version of poor communication. The absence of a universal time echoes the peculiarities of special relativity. In Einstein's universe, simultaneity is relative. Two events that appear simultaneous to one observer may not be so for another who is moving differently. Godel's universe takes this to an extreme, where even the concept of before and after blurs into confusion. The Godel universe paradox also raises unsettling questions about determinism. If the past, present, and future are all part of a closed loop, does free will exist? Are our choices genuine decisions, or are we merely following a pre-written script that loops eternally? Do we have the ability to change anything, or are we passengers trapped on a cosmic Ferris wheel? As strange as it sounds, the paradox has practical value. It sharpens our understanding of general relativity and pushes the boundaries of what is possible within physical theory. It also serves as a playground for testing ideas in quantum gravity, string theory, and the search for a unified theory of everything. Even though Godel's rotating universe does not describe our reality, it inspires thought experiments and challenges researchers to confront questions that might otherwise be ignored. Could there be pocket regions of space-time in the far reaches of the cosmos where time loops exist? Could microscopic, closed time-like curves occur at quantum scales? These remain tantalizing mysteries. For now, we experience time as an arrow, relentlessly moving forward. We cannot circle back to yesterday, much less visit the distant past. Yet the Godel universe paradox lingers as a whisper in the dark, reminding us that nature may be more flexible and bizarre than common sense allows. As you close your book and prepare to turn off the light, consider this final reflection. Maybe the reason we cannot travel back in time is not because it is impossible, but because the universe knows that no one wants to live through another family reunion twice. The antinomy of pure reason, when logic refuses to pick a side. You are staring at the ceiling, unable to fall asleep, when your mind decides to ask a completely unnecessary but oddly captivating question. Did the universe have a beginning, or has it existed forever? You try to answer. Both possibilities sound reasonable. Both also feel absurd. Welcome to the antinomy of pure reason, where the universe presents you with two choices and politely refuses to tell you which one is right. The paradox comes from the brilliant 18th century philosopher Immanuel Kant, who in his critique of pure reason laid out four antinomies, or contradictory claims, about the nature of the cosmos. The first and most famous one deals with the beginning of the universe, and whether time and space are finite or infinite. Kant's paradox goes something like this. If you argue that the universe had a beginning in time and space, you run into the problem of explaining what came before it. If you claim that the universe has existed forever, you face the impossibility of an infinite past with no starting point. It is the ultimate cosmic no-win scenario. Whichever door you open leads to a room filled with more locked doors. The antinomy works like this. The thesis argues that time and space must have a beginning because an infinite past is logically impossible. You cannot traverse an infinite series of past events to arrive at the present. If time stretched back forever, we would never have reached today. The antithesis counters that the universe must be eternal. If it had a beginning, there must have been some prior state or cause which itself must have existed in time and space. Therefore, time and space must stretch back infinitely with no first moment. Otherwise, you must explain how something came from nothing. Kant's genius was not in solving the paradox, but in exposing the limits of human reason. He argued that our minds are wired to think in terms of cause and effect, beginnings and endings. We impose these concepts onto the universe even though the cosmos itself might not conform to them. According to Kant, the problem arises because we apply categories of human understanding to something that exists outside our experience. Time and space, he proposed, are forms of human intuition. They are the lenses through which we perceive reality, not necessarily properties of reality itself. This is where the paradox deepens. If time and space are products of human perception, asking whether they had a beginning or not might be a meaningless question. It would be like asking what lies north of the North Pole. Modern cosmology, centuries after Kant, has revisited the antinomy with new tools. The Big Bang theory suggests that the universe as we know it expanded from a hot, dense state around 13.8 billion years ago. In that sense, space and time had a beginning. But physicists debate whether the Big Bang was truly the beginning of everything or merely the start of the current phase of the cosmos. Some propose that our universe could be part of a multiverse, a vast ensemble of universes, each with its own laws and histories. In this view, what we call the beginning may just be a local event in an infinite cosmic sea. Others explore theories of quantum gravity, which hint that time may not have existed at all before the Big Bang. Time itself could have emerged as the universe cooled and expanded, much like steam condenses into water droplets. In that case, asking what happened before time would be nonsensical. There was no before. Meanwhile, loop quantum cosmology suggests that the universe may have bounced. Instead of a singular beginning, there could have been a prior contracting phase that collapsed and rebounded into the expanding cosmos we observe. This scenario sidesteps the need for a true origin, but replaces it with an eternal cycle of expansions and contractions. The antinomy of pure reason remains relevant because none of these theories offers a definitive answer. They all raise new questions. Was there something before the Big Bang? Can time emerge from timelessness? Does the multiverse solve or just relocate the problem of origins? Kant's paradox also highlights an uncomfortable truth about human inquiry. We crave answers. We want a beginning, a cause, a first domino. Yet the universe may simply not provide one in terms we can understand. It may be that the cosmos does not owe us an explanation that fits neatly into our mental boxes. The antinomy also echoes in the debate over determinism and free will. If everything has a cause, does that mean our choices were predetermined by an unbroken chain of prior events? If not, how can something happen without a cause? Again, the human mind bumps against the limits of its own reasoning. What makes the antinomy of pure reason so fascinating is its gentle cruelty. It does not throw you into a complex mathematical maze like quantum field theory or general relativity. It merely holds up a mirror to your thinking and shows you the cracks in the glass. You realize that even with perfect logic, you can arrive at equally defensible but contradictory conclusions. Philosophers have wrestled with this for centuries. Some argue that the paradox is evidence that reality transcends human comprehension. Others see it as a sign that we must invent new ways of thinking to tackle the cosmos' most stubborn riddles. In a way, the paradox has a comforting side. It reminds us that uncertainty is not failure, it is part of the adventure. The joy of inquiry lies not only in answers but in the questions themselves. As Kant might say, reason is a tool with limits, and knowing those limits is itself a form of wisdom. Even in modern physics, the echoes of Kant's dilemma remain. The question of the universe's origin fuels debates at conferences, in classrooms, and under starlit skies. Every new telescope and particle collider is, in a sense, a humble attempt to peer beyond the veil of the antinomy and glimpse the truth. For now, the antinomy of pure reason remains unresolved. It stands at the intersection of physics, philosophy, and metaphysics as a quiet but persistent riddle. Will we ever solve it? No one knows. Perhaps the answer will be so unfamiliar that it will require an entirely new kind of thinking to even comprehend. As you drift into sleep, with these cosmic musings swirling softly around you, consider this one last thought. Maybe the reason the universe will not tell us whether it had a beginning or not is that it enjoys watching us argue about it. After all, eternity is a long time to be entertained. The problem of time in quantum gravity. When time goes missing. The kettle whistles softly as you wait for your tea to steep. You glance at the clock, watch the second hand sweep forward, and feel reassured that time, at least for now, is behaving itself. But as you stir in the sugar, a peculiar question bubbles to the surface of your thoughts. What if time is not fundamental at all? What if, under the hood of the universe, time does not even exist? Welcome to the problem of time in quantum gravity, where time itself decides to vanish just when physicists need it the most. In everyday life, time is the backdrop to everything. It tells you when to get up, when to work, and when to take a well-earned nap. In physics, time has been equally central. From Newton's ticking cosmic clock to Einstein's flowing river of space-time, time has always been there. Or so we thought. The trouble began when physicists tried to unite the two towering frameworks of 20th century physics, general relativity and quantum mechanics. General relativity describes the large-scale structure of the universe, stars, planets, black holes, and the expansion of the cosmos. It treats space and time as a smooth, flexible fabric that bends under the weight of mass and energy. Quantum mechanics, by contrast, governs the tiny realm of particles and forces. It describes a jittery, probabilistic world where particles pop in and out of existence and uncertainty reigns supreme. In quantum mechanics, time is an external parameter, something you measure changes against, but which itself remains fixed and reliable. Here comes the paradox. When physicists attempt to create a theory of quantum gravity, a single theory that works for both the very large and the very small, they find that time seems to disappear. The equations describing the quantum state of the entire universe, such as the famous Wheeler-DeWitt equation, have no explicit time variable. The universe, at this fundamental level, looks timeless. It is as if you opened the instruction manual for the universe and found the pages on time had been mysteriously torn out. This is what physicists call the problem of time. If time is so essential to our experience, why does it not appear at the deepest level of physical law? One explanation suggests that time is not fundamental but emergent. Just as temperature is not a property of any single molecule but arises from the collective motion of many molecules, time might emerge from the collective behavior of quantum states. It exists because of relationships between things, not as an independent entity. Imagine a book full of photographs. Each photo shows a different arrangement of objects. The book itself has no built-in sense of before or after, but when you flip through the pages, you perceive motion and the flow of time. Some researchers believe the universe works the same way. The pages exist simultaneously, but our consciousness experiences them one after another, creating the illusion of time passing. Another approach is the relational view of time. championed by physicists like Carlo Rovelli. In this view, time does not exist as a backdrop, but as a way of describing how objects change relative to each other. A clock does not tell you absolute time, it only tells you how much it has changed compared to other things. This relational perspective fits well with the quantum world, where events are often about correlations between systems rather than absolute measurements. Yet it raises unsettling questions. If time is just an emergent property or a convenient label for change, what does that mean for the past, present, and future? Are they real, or are they just useful stories we tell ourselves? The problem of time also causes headaches in cosmology. If the universe as a whole is described by a timeless wave function, how did it evolve from the Big Bang to now? How do you define before and after without time? Trying to explain the birth and expansion of the cosmos without time feels like trying to bake a cake without flour. You can try, but no one will like the result. Even black holes add fuel to the fire. According to general relativity, time slows down near a black hole and effectively stops at the event horizon. What does that mean for a quantum particle caught in the gravitational grip? Is time still meaningful, or does it crumble under extreme conditions? Physicists have proposed several possible resolutions. Some hope that a full theory of quantum gravity, yet to be discovered, will restore time in a new and unexpected form. Others suggest that time may only appear when you focus on a small part of the universe rather than considering the universe as a whole. It could be that time is a local phenomenon, like weather patterns on Earth, which makes sense within regions but not across the entire planet. There is also the idea that time and space may both emerge from even more fundamental concepts, like quantum entanglement. In this vision, space-time itself is not the basic fabric of reality, but a structure that arises from the entangled relationships of quantum bits, much like the warmth of a fire comes from the collective motion of atoms. The problem of time remains unsolved, but it has taught physicists to be humble. What seems obvious at our human scale may not hold true at cosmic or quantum scales. Time, the very thing we thought we understood best, may turn out to be one of the greatest illusions of all. This paradox also reminds us of the curious relationship between science and experience. We experience time flowing from past to future. We remember yesterday but not tomorrow. We make plans, measure durations, celebrate birthdays. Yet physics tells us that, at a fundamental level, the universe may not share our obsession with clocks and calendars. So what should you do with this unsettling knowledge? Nothing changes about your day-to-day life. Your watch will still tick, your tea will still get cold, and the sun will still set. But somewhere deep down in the machinery of reality, time might be an optional feature rather than a core ingredient. As you finally sip your tea and feel the warmth slowly fade, consider this last reflection. If time does not really exist, then you have the perfect excuse for being late to your next appointment. Just tell them you were caught in a region of the universe where time had temporarily taken the day off. The Einstein-Podolsky-Rosen Paradox. When particles keep in touch without talking. You are sitting quietly, scrolling through your phone, and you send a message to a friend halfway across the world. You expect a delay. The message has to bounce through servers and satellites before it pops up on their screen. Then a strange thought slips into your mind. What if particles can send messages instantly, with no waiting, no matter how far apart they are? Welcome to the Einstein-Podolsky-Rosen (EPR) paradox, where the universe seems to allow faster-than-light communication, or at least a very good cosmic illusion of it. The EPR paradox is named after Albert Einstein, Boris Podolsky, and Nathan Rosen, who published a paper in 1935 that became one of the most famous challenges to the foundations of quantum mechanics. At its heart, the paradox explores the bizarre phenomenon known as quantum entanglement. Quantum mechanics tells us that two particles can become entangled, meaning their properties become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. If you measure the spin, position, or momentum of one particle, the other particle's corresponding value snaps into place immediately. To Einstein, this idea was unsettling. He called it spooky action at a distance, and refused to believe nature would be so sloppy. According to classical physics and relativity, no information or influence can travel faster than the speed of light. There must be something hidden, what the EPR paper called hidden variables, that determines the outcome of measurements in advance. The EPR paradox posed a simple but devastating question. Is quantum mechanics a complete theory? If not, could a deeper theory with hidden variables explain the apparent instant connection between entangled particles without violating relativity? At first glance, the EPR argument seemed persuasive. It appealed to common sense and intuition. If two particles are separated by a vast distance, how can one know what happens to the other? There must be a local, realistic explanation. Einstein and his colleagues argued that quantum mechanics, while undeniably successful in predicting experimental results, was only an incomplete description of reality. But quantum mechanics had a different story to tell. The theory insisted that particles exist in a superposition of states until measured. Only when observation takes place do the possibilities collapse into a definite outcome. For entangled particles, this collapse seems to happen simultaneously, even across vast distances. Decades later, the debate took a dramatic turn. In the 1960s, physicist John Bell formulated what is now known as Bell's theorem. Bell showed mathematically that if hidden variables existed and obeyed the rules of local realism, certain inequalities would hold in experiments. Quantum mechanics predicted violations of these inequalities. Starting in the 1970s and continuing into the modern day, experiments have repeatedly confirmed the predictions of quantum mechanics. Entangled particles violate Bell's inequalities, leaving no room for local hidden variables. The spooky action at a distance is real, or at least real within the strange rules of quantum physics. The paradox then deepens. How can this be? Does it mean that information travels faster than light? Not quite. Quantum entanglement does not allow you to send usable information instantaneously. The outcome of a measurement on one particle is random, and you cannot control what you get. Only by comparing results later do you see the perfect correlations between particles. There is no way to exploit entanglement to cheat the speed limit set by relativity. So, what is really going on? The EPR paradox remains a vivid demonstration of the tension between two cherished principles: locality, things only affect their immediate surroundings, and realism, things exist with definite properties, even when you are not looking. Quantum mechanics forces you to let go of at least one. Many physicists have accepted that nature is non-local at a fundamental level. Entangled particles do not care about distance the way humans do. They behave as a single system, regardless of space between them. This does not violate relativity because no usable signal passes faster than light, but it still feels deeply counterintuitive. Others explore the idea that realism must be abandoned. Perhaps particles do not have definite properties until they are measured. Reality itself might be probabilistic and observer-dependent, an unsettling but increasingly supported viewpoint. The EPR paradox also ties into one of the hottest areas of modern physics: quantum information science. Quantum entanglement forms the backbone of emerging technologies like quantum cryptography and quantum computing. Entangled particles can be used to perform tasks that would be impossible using classical systems. Quantum teleportation, for example, uses entanglement to transfer the quantum state of a particle from one location to another, though not the particle itself. This does not send matter or information instantaneously, but it showcases the strange interconnectedness of the quantum world. Philosophers and physicists continue to debate the meaning of the EPR paradox. Some propose that reality itself may be holographic, with entangled correlations arising from deeper hidden connections in spacetime. Others explore exotic interpretations like many worlds theory, which suggests that every possible outcome actually occurs in branching universes, and entanglement simply reflects which branch you observe. Despite decades of experiments, the EPR paradox has not lost its power to provoke wonder. It stands as a gentle but persistent reminder that the universe does not conform to human expectations. Our classical ideas of cause and effect, proximity and separation, certainty and randomness are all upended by the delicate dance of entangled particles. Even Einstein, though unconvinced, acknowledged the beauty of quantum mechanics' mathematical structure. His skepticism laid the groundwork for one of the most profound explorations into the nature of reality ever undertaken. Today, the EPR paradox is celebrated as a cornerstone of quantum mechanics. It remains unresolved in the sense that we do not yet fully understand why the world behaves this way. But we know, beyond any reasonable doubt, that it does. As you set your phone down and prepare for sleep, let this final thought float through your mind. Next time someone ignores your message for hours, just remember that even entangled particles cannot send texts faster than light. Patience is not just a virtue, it is built into the very fabric of the universe.